models as we get there. But again, my philosophy is that if you understand the basic models well, only then you'll understand the advanced model. So let's spend a little bit of time on some of these frameworks. Again, if I'm going faster, please feel free to stop me, ask questions. Okay. So in this module, we'll talk about methods that are useful for data analysis. Again, we're talking about these methods in the context of public transit, but you can apply these methods widely. You can apply it in transport safety, you can apply it in travel demand modeling, and various other contexts. So any data that is of this form, you can use this method. So some of these methods have application outside transportation also. There are people in marketing, biostatistics, and other fields who are also using some of these. So we'll start with the simplest of all the methods, the linear regression model. Again, most of you would have seen this, or even if you did not estimate it, you would have at least used it in application. So in regression analysis, what we're doing is you have a continuous variable, you have a dependent variable such as number of trips or vehicle mileage or income or various variables like that. So they become the y, and you are trying to relate that to different independent variables. Independent variables could be, for example, if you're modeling income, education level, age, gender, kind of industry they work in, all of these could be independent variables. So you simply write y is equal to beta naught, a constant, plus beta 1 x1 plus x2, and so on. So it should look something like this. So this is how the equation looks like. And we are trying to figure out from the data what the values of betas are. Okay. So if you look at your data set, you will have an important aspect of linear regression is that none of these coefficients can have powers. So the betas cannot have any powers. X's can have powers. If you want to use time square, that is okay. You can take the square of the variable and use it as a new x, that is still linear. But you cannot have powers for this coefficient. So if you have a relationship like this, on first glance it might appear like you cannot do a linear regression model because you have powers there. But what you can do is take the log of this, and once you write it in this fashion, you will write ln x1 as a new variable x3, ln x2 as a new variable x4, and this is your beta naught or constant. So then this becomes a linear regression. But if you cannot transform in this fashion, and it can happen in some cases like that, where you still have x power 1 by alpha or something like that, beta power 1 by alpha, in that case, you cannot apply linear regression. But you can still apply non-linear regression approaches. They are not, they don't fall into the linear regression. So this is an example of a log linear model. Again, in the example I showed the data in the last afternoon session, we took log y because y has a very large range. We made the range smaller by taking the logarithm of it, and we used it. You can also use other forms of linear models. So the simplest form of a linear regression model is a binary regression model, where you have only the constant and one independent variable. Okay, so I only have x as an independent variable. So for example, y is the number of trips generated, x is one exponential variable, beta naught and beta 1 are coefficients we want to estimate. So y is known to us. Okay, we collected data, we have information for, let's say, 1,000 people. What is their observed number of trips? We also collect their x. Okay, so independent variable x, here in this case is one exponential variable. Let's say it is how many cars they own, for example. So you have a column of y's, you have a column of x. What we are trying to figure out is the values of beta naught and beta. Okay, these need to be estimated. We don't know beta naught and beta. Okay, so usually we do this using data, and because we cannot collect data for the entire city, let's say we look at this at a trip generated by a household, we cannot collect data on every household in an urban region, so we do sampling. So what happens is when you take a sample, you cannot have 100% confidence and say, oh, this coefficient is 3.8. You could do that if we collected data from the entire population. If we collect for the entire population, then the coefficients that we estimate are what are called population parameters. Okay, but because we do sampling, there is a possibility that our sample might be representing the population, but there are variations. It's not like you're doing it for the full sample. So if I change my sample, let's say I collected 1,000 data points, and then I go back in a couple of days and collect another 1,000 data points. Now, if I estimate by beta naught and beta 1, will the beta naught and beta 1 be same across the two samples? They will be different. Okay. So it's not enough to know what the value of beta naught and beta 1 is. We also want to know what is the variability of beta naught and beta 1. What I mean by that is, so I spent 1 crore rupees collecting data. I built a model because I have 5,000 household samples. I did a lot of work based. Now, if all I know is the coefficient values, if somebody else collects another set of database data, the whole project should not be a because your coefficients are at the end of the day random numbers because it's tied to the same. I take 5,000 households, I get beta naught and beta 1. It could be, let's say, 1.5 and 2 points as an example. If I take another 5,000 sample, again, I'm not saying it will become minus 1.5 and minus 2.5. It won't become that way, but it could be 1.3 and 2.7. So what we are seeing is there is a population value for the coefficient, but because we are taking a sample of observations, we are trying to get as close to the population value as possible, but recognizing that there is some variability in the coefficients. So in addition to recognizing and evaluating the value, we also would like to estimate a confidence interval on the parameter. That is important because if the confidence interval, if your parameter is such that it can vary a lot, that is not very good because if sample 1 gives you 1.5, sample 2 gives you minus 1.5, sample 3 gives you 2, sample 4 gives you minus 2. If you get a variable like that, that variable is not really useful because it is changing, the coefficient is changing with the sample. So that tells you that the variability for that coefficient is too much and that variable should not be used in your model. Okay. So while the most important part in any model is estimating the coefficients, it's also very important to understand whether those coefficients are stable or not. Okay. So we call this, are we able to pin down the parameter efficiently? That's what we're trying to do when we estimate models. If you are not able to pin down a parameter for a particular variable, maybe we should drop that variable. Okay, so that's what we'll be talking about as we go. So we'll write this in matrix form because most of the operations are connected in matrix form for all models, linear enrichment. So here, if you have a coefficient system like this, this is called a multiple linear enrichment model because I have more than one independent variable. Okay? So here I have x1 through xk, independent variables. The corresponding coefficients go from beta 1 to beta k. This epsilon is the unobserved error or noise in your data. So what happens is you assume that epsilon follows a normal distribution and the sum of epsilon across all the records goes to 0. So there is noise in the data, but it is unobservable noise. Okay, if it is observed, we can calculate it as one of the independent variables. So the mean of epsilon is 0. Okay, there is a standard deviation we estimate. Okay, so here I am just writing this equation in the form of matrices here. So y includes n observed values of y. X will have a column of constants and x1 through xk as columns. Okay, each of them again will have n rows. Beta is just beta naught to beta k, so you have k plus 1 parameter here, and then you have epsilon going from there is 1 per record, 1 to. Okay. So now I can write this equation like this. It's simply y is equal to x beta plus epsilon. Okay, I'm just multiplying the matrices. Y, you get x beta plus epsilon. Okay. Now this is the true population beta. Okay, even in the true population beta there is an error. But when we try to estimate it, what we do is we replace y with y hat because y hat is what is used to represent the prediction from our model, and beta hat will be our coefficients we estimate. So we call it y hat will be equal to x beta. Okay, so we're trying to get to this. So now what we want is Yeah, it is because yes, it should be 1 because beta naught multiplied with 1 by. Okay, so beta naught is your coefficient. The independent variable, implicit independent variable there is 1. So that's why this is column of 1s. Okay. So now you can write this as y hat is equal to x beta hat. And how, whenever we have a data, so let's say I give you a data set. I have column like this where I'm telling you what the y's are. So let's say this is number of trips 6, 5, 3, 12, 8, 7. You have that data for this. And x1, x2, x3 could be number of people in the household, number of cars in the household, location, whether it's urban or rural location, income level. So all of these could be your independent variables. Now, how can you find the betas? What will you try to do? How can you solve for betas? Can we simply do a system of equations and solve for them? Why not?
It becomes very complex to solve with a lot many
Okay, so basically you have n rows of data. So usually n will be in the order of 100 or 1000, right? So you have 1000 equations. There are only probably 10 unknowns. Okay, so it is an overly defined system of equations. So you will not have a unique solution. If you try to find the 10 parameters, you will not be able to find because you will have infinite number of possibilities that you look at. So what we are trying to do is we won't be able to solve it as a system of equations. So what we'll say is, okay, I know I cannot find a perfect solution because there cannot be 10 values that satisfy all 1000 equations. You won't be able to find them. So what we do is we'll say, okay, let me try to get the next question possible. What we can do is my prediction error should be as small as possible. Right? So I want to find 10 values. Yes, it won't, I mean, if you get lucky and it perfectly matches all 1000 records, great, that's your solution. But it usually does not happen. In real world data sets, it never happens. So we started, okay, let me try to minimize my error in the prediction. So because again, at the end of the day, the reason we're developing these models is to understand the relationship between y and x. So we want it to be as accurate or as close to the reality as possible. So we simply start with minimizing y minus y hat. Y is the observed value. Y hat is computed as x beta hat. Okay? Like this. So our error is simply this. Our objective now becomes minimize that. So should I just minimize y minus x beta hat? If I directly minimize the difference, some of the differences will be positive, some of the differences will be negative. So when you add it, everything will become 0, right? So you don't want to do just the direct difference. So we use the square difference to ensure that both negative and positive are penalized. Okay. Now, one part is, okay, why can't we use an absolute function? Okay. Theoretically, that is also valid, but I don't know if you guys remember your calculus enough. If you do differentiation of the absolute function, around 0, it's a discontinuous function. And discontinuous functions don't work well. So we don't want to do anything with discontinuous functions because it breaks down all the asymptotic theory that we use. So what we'll do is we prefer the square. Okay. Theoretically, you could have tried with absolute also, but the square works better. Okay. Because square function is continuously differentiable. So you can take the first derivative, second derivative, whatever you want, you can take, and that helps us in some estimate computation. So what I'm doing here is, so we'll take the square. So in matrix notation, square is nothing but transpose times the other one. So it is y minus xb hat transpose times y minus xb. Okay, so this would be what we're trying to minimize. Trying to minimize, I want to find a beta hat that minimizes the difference between the observed vector of y's, and the predicted vector x beta hat. Okay. So I want to solve for beta hat that gives me the least error in that data set. Every data set might have differences. Okay. So again, because it's a simple function, you start with minimization. I'm just expanding these terms. I'm just multiplying the matrices here, and I'm expanding this. And then, because it's a minimization, I'll try to differentiate with respect to beta hat because I want to estimate beta hat. I want to find out what the value of beta hat is. So I'll differentiate this term these three terms with beta hat. The first term, y hat y, is the observed number of trips. It has nothing to do with beta hat. It's a constant. So when I take the derivative of y hat y with respect to beta, it will be a 0. Okay? Everybody okay with that? Because y is the data. This is given to you. This does not change with beta. Right? So this is known to us. X is also known to us. So these are observed information. So if I take, so these two will be constant in our equation. So when I come to take the derivative of this function, derivative of this will be simply 0. Okay? When I come here, I only have beta hat. This can be treated as a k. It's a constant. Right? X dash y is a k. So derivative of beta hat is 1. So you'll get 2x dash y here. There is a square of beta hat here. Effectively, when you take the derivative of that, you will get 2 beta. So you get 2x dash x beta. So this, on the other side, we set that, we take the derivative and set that to 0, right? So we're setting that to 0. So now you get 2x dash y is equal to 2x dash x beta. What I need, I want to find, you can cancel the 2 off. I want to find the beta hat. So I pre-multiply x dash x on both sides. So I just want to make, so I sent this that side. So x dash y was there here. Then what I did is, I cannot just do 1 over, so I have to do inverse because it's a matrix. So I multiplied this with x dash x whole inverse in the front. So this becomes beta hat, and I'm multiplying that. So you get a formula for beta hat, which is a function of x and y. So I know x, I know y. So I can find my beta hat using this formula. All I have to do is do some matrix multiplication inverse. Clear? Any questions? So if you are given your columns of data, if you have your y and x, you can find beta. You just need x because you just need to compute x dash x whole inverse x dash. And again, that's formula is very easy to remember. And you'll notice this is the only model which has the formula for beta. Okay, every other model is too complex to be able to solve in this fashion. You won't get a solution for your issue. So your beta hat has a clear solution. Anybody does the model, any software you use, you should get the same result. To the third decimal, fifth decimal, whatever, but it's hard beyond that. Okay?
Y hat y minimum function. Yes. Y dash y. Y is a constant. However, y dash is actually in terms of x and beta.
No, not y hat. Y. Y is still a constant. Yeah, so y dash also, so it's just, instead of putting it as a column, y dash is a row. So y dash y is also a constant. So let me give you an example here. So let's start with a simple y and x. Okay. So let's say I have y. My model is y equal to beta 1. So there are no independent variables. I just have a constant. So a vector of 1s. So my x would be this. Everybody okay with that? Okay. So now in this case, let's try to find what is beta 0. Okay. So beta 0, beta is x dash x whole inverse x dash y. So I have x. What will be x dash? X dash will be a row of 1s. Okay. So row of 1s times column of 1s. If I multiply both of them, matrix multiplication, 1 times 1 plus 1 times 1 plus 1 times 1 n times. So it will be n. Okay. So you see that here? Everybody okay with that? So x dash x is n. X dash x inverse will be 1 over n. It's only a scalar, so its inverse is just 1 over. Then let's do x dash y. X dash y is again vector of 1s times y. So 1 times y1 plus 1 times y2 plus 1 times y3 simply be y1 plus y2 plus y3 plus y. Okay. So you end up with summation of y. So now let's apply the formula x dash x whole inverse x dash y. So this is n. Inverse will be 1 over n. This is summation of all of that. What does this show you? What is 1 by n over sum of y? Simply the mean. Right? So if you want to know what is the constant in your data set without any independent variable, just take the mean. You take the mean of your y, that is your constant, and this would be the dumbest guess we can make. If I give you a data set and tell you these are the trips people the number rate of trips people are making. If I tell you, okay, a new person is being brought into this data set, what would be your guess? You should say, yeah, take the average of what is observed right now. That should be our starting. Now, why is this important? Because any so-called model we develop should give me an error less than the error from this term model. Otherwise, why do I need your model? If your error is more than this, I don't need that model. I can blindly tell you what the answer is. Okay? So that is why we start with this. Because this gives you the average number of trips. So if the average you observe is 3 trips, if a random person is brought into the list, your starting point will be, yeah, this person also will make 3 trips. Because that is the estimate we have based on the data. Okay. Now every time you add a new variable, you should be improving your error. What I mean by improving the error is reducing. So you want to make the error smaller and smaller. And this becomes our benchmark model. Any estimation we do, we come and say, okay, this gives an error of 100 units, let's say. So if I do a new model with 5 variables, if it gives me more than 100 units, don't even tell me what you did, throw it at it's wrong. Okay, if it's less than that, then I'll start thinking about, okay, you got 95, okay, I'll think about whether it's good enough or not. But you have an upper bound on the error, and this is what forms the basis for any goodness of fit measurement we do with these models. Okay, any questions? Okay, so I'll show you an example model run and desktop in my office. And how many of you use remote desktop? But I love it. I connect from anywhere, and so I know where everything is on my. I have some OCD on that, so I have my computer and I work only on that. Simple data set. I'll just show you model. I'm running linear regression. I'm modeling number of trips. So this is my dependent variable. Then output size and then number of paths from variable. So again, in this case, it's just running it in this fashion. I want to show you some outputs. I'll keep showing you this again, but we'll get back. Here, this is where the coefficients are printed. So you get a value for a constant which is minus 0.232. Number of persons in the household is 2.184 coefficient, and number of automobiles is 0.826. Okay, so this is what I'm showing you. So what that means is, interpretation wise, we can start with, as the number of people increase, what should happen to number of trips? Okay, it should increase by 2.18. Okay, yeah. So what this tells you is, first thing we are looking at is, okay, it has a positive effect as expected. As the number of persons increase, the number of trips will increase. Same thing with number of automobiles. More cars, more trips people need. Okay, and both are positive. Now, one of the things to understand is, so far what we did is I solved for these values, just doing x dash x whole inverse x dash y for these 3 columns. You have a column of ones, column of households data, column of automobile data for each household, and you have the y's. We use that and got it. But what we have not talked about is Okay, how do I know if this is statistically significant? All of you have used that word, and you would have written papers also. What does it mean to define it that? Okay, so for that we need to understand, again, as I said, these are random variables, which means they have a distribution, they have a mean and a standard deviation. The interplay between the mean and standard deviation determines whether that coefficient is significant or not. Okay, so that's what I want to talk about. It is something not very complex, but I think it's important to understand this as we move forward. So I'll show you some things here. We have a normal distribution function because we are assuming that our error term is a normal distribution function. A normal distribution, so I'll show you some characteristics. Again, nothing to memorize. It's a probability distribution and a cumulative distribution for them. This is how a normal distribution would look like, right? So depending on different needs, so I have three distributions centered around 0. It's a symmetric distribution, nice bell shape. If the variance is small, okay, sigma square equal to 0.2 here, the variance is that it hugs around the 0. Okay, so you see that when the variance is 0.2, everything is very closely around the mean. When the variance keeps increasing, the height of the curve keeps coming down. Basically, I'm hitting it from the top, like I'm making it wide, right? So I'm banging it down, it keeps coming down. The higher the variance, the lower is the height, and we have larger spread. Okay? Here, the green one is simply another example where I moved the mean. I moved the mean to -2 with particular variance of 0.5. Okay? So again, this is just to show how normal distribution would work. Now, if our parameters are random variables, okay, which means they have a mean and variation, which would you want them to be? You want them to look flat or tall? What would you want from your parameter? Right? You want them to be tall because that means they have a very narrow range. The predominant number of density of these values will be around the mean. What we are estimating in our model is the mean. Okay? So if they are flat, like this for example, the mean is 0, it can go with significant probability to -2 or +2. That's too much variation. But if it is tall, okay, we got it 0. Okay, it can go with some probability to -0.5, +0.5. That is close. So that tells you this relationship has some promise potentially that you can capture. Okay, so I'll formalize that. That was the PDF. This is the CDF. So again, some more characteristics. So if you have mu and sigma as your mean and standard deviation in normal distribution, if you go 1 sigma to both sides, okay, from the mean, you're traveling 1 sigma to the left and 1 sigma to the right, that will capture about 68% of the observations in that distribution. If you go to 2 sigma, you will cross 95. If you go 1.96 sigma, you will get 95%. If you go 3 sigma, you get to 99.7%. Okay. Obviously, how much distance do you have to go to get 100%? Can we ever get 100%? No, right? Because infinity. If somebody tells you I am 100% sure this model works better than something, yeah, they're lying. Nothing in statistics is 100%, right? That's a good thing and bad thing. Because of that, you also can use statistics to say whatever you want to say, but usually you can never say anything with 100% confidence. The higher the confidence you want, the width of the distribution keeps increasing. Okay, so if you want to be confident at only 68%, I'm only going 1 sigma on both sides. But if I want to be confident at 99.7%, my distribution goes 3 sigma on both sides. So the larger the confidence you want, the higher is the width of the confidence. It looks counterintuitive, right? Like, if you think about speed, you're doing a study of speed on the road, and you want to tell 90% of the time what is the speed limit versus 95% of the speeds observed, and then you want to do it 95% of the time. You want to do it 99% of the time. Each time you want higher confidence, the band keeps becoming larger and larger. Okay, so you might say at 99%, the distribution I see on the road goes from 20 kilometers to 60 kilometers. That's not very useful, right? After a point, the band becomes pretty useless because you're saying, I'm going from 0 to 100. I mean, what kind of information is available in that band? Everything physically possible is part of the band. So that's why you have to, there is a trade-off between what kind of confidence you want and what will be the output that you want to get. Okay. So let me show you an example there. So I want to show you this one. So let's say we have this as our equation. So the true equation for this case, let's assume, is the number of trips is a function of household size and number of cars. Okay, only two variables. So now what I want to understand is whether beta 1 and beta 2 are significant. So in hypothesis testing, we start with the assumption that variable has no impact. Okay, the idea is you want to prove to me beyond doubt that this variable has an impact on my life. Okay, you are not saying, if by default you are not assuming that a variable is important. So you might say, oh no, household size should be important. Okay, then let's prove it. Only if you prove it, it's like the court of law. Okay, everybody is presumed to be innocent. Okay, even if they are Donald Trump. So if only you have to prove, I know it's recorded. You have to prove it beyond doubt that that person is that committed the crime. Okay, so same thing in statistics. Everything has no impact. You have to prove beyond doubt that that variable has an impact. So that way, we are ensuring that we are not taking every variable that pops up in your model as important. We are actually ensuring that we have a high level of quality control to make sure these variables are really significant. Okay, to do this, so let's say we have this variable. So you have the coefficient, which is our mean, and you ended up, you computed a standard error. This is computed in SPSS for us. So we have this value in any software for that matter. So if I plot this distribution, so this is the standard error, so variance would be square of that. I plotted this distribution. What you will notice is predominant area under the curve is to the right of 0. Right? So it's actually 90.998. So 99.8% of the curve is to the right of 0. This is kind of a good variable for us. Okay, because what it tells you is the coefficient is very likely to be positive. Okay, so if I want to do a confidence band of 90%, I can clearly say 90% of the time this coefficient is to the right of 0. So this is a positive coefficient and a significant coefficient. Okay, now another example. I just flipped the sign. Okay, so I put this mean as minus 1.5. It does not change anything. Only thing that changes is the coefficient is completely negative. So this would be a negative coefficient, but again statistically significant. Okay, now if you go to another, I increase the standard error to 1 point. Okay, on first glance, what you will notice? Again, predominantly positive. Right? A large portion of this distribution is also positive. In fact, it is about 0.89%, 89% is positive. 11% is negative. Okay? So, in this case, we reject that this is a significant thing. Again, the idea is, let's say my confidence interval is, I'm putting a limit as 90%. So, at least 90% of the curve should be to the right of 0 or left of 0, depending on the coefficient. If the mean is positive, you have to be to the right. If the mean is negative, you have to be the left of 0. But if it crosses that 10%, the area on the other side, we'll say no, this coefficient is not reliable. We don't want to use it. That is the idea of what we are doing when we do confidence testing or completely statistical. So what we are checking is how much area of under the coefficient crosses 0. Okay, this again. If you look at it, many people who don't look at statistics will say, oh no, but 90%, a large portion is to the right. Why are you ignoring it? Because the reason is because if I take another sample, this reduces the, having this area here, reduces the chance that this comes significant in another sample also. So you can think of it as, if I take 100 samples of 1000 records and estimate coefficients, only 89 of them will have this parameter as positive. In the other 11, it will be negative. I don't want such coefficients. I want coefficients that are of the same sign at least 90 times. Again, because I put confidence limit as 90. If I want 95, obviously this will be even worse, right? If I want 95% confidence, this will be even worse. But the idea is we are trying to find coefficients that don't work just on that data, but they work on every other. That's where the variation and standard error comes into the picture, because we want to make sure this standard error tells you how confident the data set is on the value that we are arriving. If that confidence is lower, then that tells you that, okay, if you take another sample, maybe this won't come significant. We don't want coefficient like that. We want to be very sure that this coefficient at least will come 90 times or 95 times or 90, depending on the case, right? If you're modeling travel behavior, number of trips, 90% accuracy, 90% confidence limit is okay. But if you're, say, investigating a drug for cancer, okay, there you don't want to say, oh, I don't get 10 people will die, that's okay. It works on 90 people, the other 10 will die. You don't want to do that. So what you do there is you have a higher requirement, confidence band. It would be 99.9 in that case. Okay, that makes it harder to pin down. So only very strongly significant drugs will be selected, right? Even with that, right? even if you think about it, 99.9, especially when you're running models, you won't get coefficient significant if you put 99.99 as your significance level for your estimation. But for million people that take a drug, if you don't put it at that level, you still are losing a lot of people. So it's associated with life, right? If we get number of trips wrong, yes, there are consequences, but they are not life and death consequences. So we can live with 90 or 95. So we need to be careful by context on what should be the confidence level that you want to stick. So here I am showing the relationship with 90, 95, and 99 here. So for 90, this would be the 95%. The area would be 1.96 to 1.96. Okay. For 90%, it would be 1.65 to 1.6. As we go larger, obviously. So, but when you run the models, I mean, nobody is doing this, drawing the area under the curve. It takes a lot of time to do this, right? So you don't want to do that. So there is an efficient way of computing it. What you do is you compute the ratio of the coefficient and the standard error. So, for example, I just need to take 1.5 divided by 1.2, okay, and take the absolute of it. If that crosses the 90% level or 95% level that you're trying to look for, then you can say that coefficient is significant, otherwise it's not significant. The reason we do that is if this ratio is less than more than 1.96, it will ensure that the curve is to one side, right? Because when I move 1.96 sigma to the left or to the right, I will not reach 0. So mu, you can think of it as mu plus or minus. If you're doing 95% confidence level, we're doing this. Okay, so if your mu, let's say, is 1.5 and sigma is 1.2. Okay, so when I do 1.5 plus 1.96 times 1.2 plus or minus, the minus will take it to negative value. It is roughly 2. So it would be something like minus 0.9 for the negative side and for the positive side 3.9. Again, I'm approximating it. So once you get a negative value, your variable has a problem. So you have both positive and negative. So that means your curve is crossing 0 with significant area. Again, I'm not saying it's 50%, but it is a significant area. So whenever there is a sign change in this confidence band, we have a problem because it's crossing 0. The 90% area also has 0 within it. Okay. Again, is everybody getting that or not? Let me show you. So, if you take another example, let's say 0.3. Okay. So in this case, plus or minus 1.96. So if you do this band, so the lower end would be the minus, so 2.6, so it would be 0.9. So this is an ideal variable, right? So what we are noticing here is The lower limit is 0.9, upper limit is 0.21. This covers 95% of the area. Okay, so this is an example of a variable which predominantly stays to the right up to 95%. Now, if you have this one, it's this one minus 0.9 to 3.9. So in this case, the 95% area covers minus 9 to 3.9. So there is a good probability that it is negative sometimes, it is positive other times. So this is not a good variable. So if it is, okay, the question probably is something like what if this is 0.0, right? Yes. So the instead of meeting 95%, it is 94.5%. There you can make a judgment call. That is fine.
Would we reduce the confidence interval depending on context and
Yes. So you can. What typically like I do again, there's like I said, it's statistic. So there's no rule that you can force on anybody. But what you can do is you can say I'm looking at 95% as my confidence level, but this variable missed it a little bit. But because I think previous literature has also shown that this variable is significant, and we are retaining it for this purpose. You can justify that. Again, at the same time, you don't want to. You're going for 95 everywhere. You don't want to retain something at 83%, but 94, 93, you can make it. So we have retained sometimes insignificant variables at 80% also, but you need to make a case for it. Obviously, a reviewer will ask, and also you have to support why you're. But for theoretical purposes, this is how we.
is it statistical justification is more important of the context and the context and
Context and subject knowledge is trumps statistics all the time. It should. Okay, there's no substitute for context and understanding of the problem. Okay, for example, if you're running a safety model and AADT comes out, annual average daily traffic comes out to be significant on the road, that doesn't make sense. I mean, how can you say if traffic increases, crashes will reduce? That doesn't. So you need to recognize those things. So subject expertise is always valid, and you need to think about capturing the variable different. Okay, so statistics is a supporting mechanism for what we are trying to do. But there are some rules that you need to be careful, and if you understand them correctly and violate them, it's okay. The problem comes when you don't understand and then violate. That's why we want to understand this well. So if now you're making a case, yes, I understand it. It should be it should be less than 0, but a little bit of it is on this side. So you know what is the consequence of that error or that violation, and still you are willing to take the justification to provide a justification to control for that. That is how you should do. Okay. So now, instead of trying to do these two numbers each time, what I'll do is I will do this. Okay, so this is the easier one. So 5. It's 5 by 4, right? So this is 1.2. So this value is smaller than 1.96. So this will fail the test. This value, the 5, is more than 1.96. So this will pass the test. So again, we started with the curve, we started with positive, negative, but again, we can't do all of this each time you run our model. So we simply do compute beta over sigma and compare it to if it's greater than or equal to the T critical. So for 95%, this would be 1.96. If it's greater, then it's significant. If not, it's insignificant. That's the test that we do. Again, these numbers are provided as columns. Any software you run, they'll give you the beta, they'll give you the column of standard errors, and they compute the statistic for you. They take the ratio of those two terms and give you that. You just have to check whether it's greater than 1.96 or not, or 1.65 if you're using 90%. Okay, so this is how we do hypothesis. Yes, sure. Again, this is people are used to doing rounded percentage of the day, so they use that. There is that does not preclude you from considering impacts. And so if you're doing 90, right, if something is like 91 or more, you are not throwing it away. Right? Everything above 90 is considered. So 91, 92, 93 are also considered. So just people prefer the rounded values. Yes. So you have to mention exactly what you're using. Okay. So if it is significant at 91, so you understand the question between 90 and 95. Okay. So sometimes some variables are significant at 95, they are not significant at sorry, they're significant at 90 and 95, but some are only significant at 90, they're not significant at 90. A better way would be to indicate the retain all of them and say they use the stars approach. They put 1 star, 2 stars, and 3 stars. So 3 stars for variable significant at the 99%, 2 stars for variable significant at 95, 1 star for 90. So you are retaining everything beyond 90. Okay, that would be a better, that is more accepted way of reporting your results than trying to change the content. Because people are used to using, yeah. So this is I have slides where I show how to compute the test, and these are the bands, the confidence levels. We have 90, critical value is 1.65. It keeps going up as we go in terms of the percentage confidence level. Okay, so the mean computation is beta over standard error. So beta is the coefficient, mean over standard error. So in the yesterday's file I showed you, this is your beta, this is your standard. All you're doing is the ratio, which is computed as the distance. So you see for the number of persons, the t statistic is 23.9, which is more than 1.96 or even 1.65. Similarly, the other one also, you'll see that this is 6.5. So these are the values we are talking. Okay, and in SPSS, you get a significance column, which tells you that significance is less than 0.001, which means it's significant at 99.98. Okay. So this information is available in any software. Okay, you have the coefficient, standard error, and exponential. You can use the software appropriately that you're doing with to get that. Any questions?
Actually, I did one report. Its values went from minus 1.96 to plus 1.96. Only should be greater than 1.9.
I'm taking the absolute value. So they go, it should be greater than, if it's negative, it should be greater than minus 1.96. If it is positive, the beta, it depends on the beta, right? The beta is positive, you are making sure the whole thing, it doesn't go negative. The coefficient doesn't go negative. If it is, the coefficient is negative, we are looking at the other side. We are saying plus mu plus 1.96 sigma should be less than sigma. Okay, so to avoid that confusion, you take the absolute value. So we put t statistic as an absolute value. You won't see anywhere that this being negative. Or the absolute as p here, but we are comparing it to t critical by taking the absolute value, that everything is just value. The t statistic will be negative when you have the coefficient as negative, but t critical is always positive. That's how you compare it by taking the absolute. Yes, if the coefficient is negative, beta is negative, significant value will not be negative. Sorry, no, significance cannot be negative. It will be 0, which means it's the t statistic is so small that you have no explanatory power from it. So the larger is the t statistic value, the larger is the explanatory power of that variable. Right? If you have very high t statistic, it tells you that the curve is very tall. If you think about the distribution, so tall that you don't have any variation. It's actually very perfectly thin around the mean. So this is the, so I'm showing you the curve here. So 2.184. If you look at the confidence interval and use that, so you get this fact. So you're saying the coefficient varies only between 2.005 and 2.6. So what this tells you is, if I take 95 data sets and estimate the same model with this variable, they will range between this, which is a very narrow range, which tells you that the coefficient is significant. Same thing for this is the 90% for the same. So 90% will be a smaller band than the 95% because your T critical is smaller, 1.96 to 1.6. Okay. Any questions? So now we'll talk about goodness of fit. So again, as we talked about, we need to figure out when the model is doing well and how do we compare. So there are we started with, we can identify when a single parameter is significant or not, but we need to know, okay, how about the whole model, right? So for this, we have three elements that we model.
Should be ranging from minus to 2.6, in real world it cannot be minus.
No, I mean, some variables are negative. All we are saying is the coefficient should not change sign across samples. If for example,
Here we are actually doing mu plus something in the sigma, is actually we are estimating the expectation based on the mu and sigma value at a particular confidence interval.
yes,
So we are getting the mean value of something which we are interested to find.
yes,
So when it is we are ensuring that it stays on the positive side only mean side, because in real world we don't have any negative values.
no, we are ensuring it stays on one side. I'm not biased about positive or negative. All I'm saying is majority of the value should be towards one side. Then I know it is impacting in a particular. See, if I have a variable that is 50% positive and 50% negative, I have no idea what the variable is.
We are interested in direction in which the variable impacts the.
Yes, the dependent variable. Yes. So if I have, for example, I'm modeling number of trips and I'm looking at number of cars. As number of cars increases, I expect it to have a positive impact. So I want the entire distribution to be to the right of zero. Right? That way, it's all positive. If it is 70% positive and 30% negative, maybe number of cars is not.
Instead of number of trips, it is number of trips by public transport and number of cars, then it should have been the other way.
Exactly. So then you want the whole distribution to be to the left of. So now we want to look at goodness of it. So for that, we talk about three Y's. So there is the observed Y, the predicted Y, the average Y. Okay. So we call SST. This is the total error in our model. Remember when we started, we said the dumbest guess is the average. So the total error in your model is given by this equation. Observed minus average. Okay. Then SSE is the remaining error. Okay. So find my. And the third one is SSR. Let me write all of these elements. Okay, there is summation of all of these. These are summed across. So there are three terms. SST, this is the total error. Okay, so it is between observed and the average. Okay, so Y and Y bar. SSE is the remaining error, or sometimes it's called sum of squared residuals. Okay, so this is, we have developed a model and this is the remaining error. This is our prediction from the model. This is the observed. So difference between the observed and the predicted from your model. This is called sum of squares, squared errors. So this is called errors. is the value added by your model. I am looking at y hat minus y bar. How much of the error are you able to explain? This is called sum of squares regression. Okay, so SST will be equal to SSE plus SSR. Okay, total error is remaining error plus the error I am able to explain. So ideally, we want this to go up and this to go down. Because this is the remaining error, we want this to be 0 if we can, this to be equal to SST. That would be our goal. Okay, if SSR goes up, it's good. If SSE goes down, it's good. And now, using this, we define R square as SSR over SST. Okay, so this is what we get in terms of improvement versus total error. Now, if my model happens to be the average model, okay, y hat will be same as y bar. Okay, in that case, SSR will be 0. So that will be the lowest point for R square. R square starts at 0. And if your y hat is a perfect model, okay, y minus y hat will be 0. If I have a perfect model, if I am able to perfectly predict everything, SSE will go to 0. So SSR and SST will be equal. So R square will be. So if you have a perfect model, R square will be 1. If you have the dumbest model, which is just the average model, that will be 0. So your R square will go from 0 to 1 based on this. Okay. Again, sum of square residuals is also printed if you are running linear regression. R square is computed in your software. It's available to you to use. Okay. Does this make sense? Any questions? Yeah. So R square equal to 0, SXC is equal to 0. Yes. There's issue with data. So there is an issue with some. It can happen that in some cases you will get coefficients which are contrary to what you expect from. Okay, it can happen. I mean, there are a lot of data sets where that happen. So some of the things you can do is look at the relationship excluding everything else first. Okay, so for example, in your model, maybe there are other variables that are closely interacting with population. So that could be creating an issue. So if you start with only number of cars and one constant and population, maybe it will be positive. And as you keep adding, it flips at some point. So don't add the variable that is making it flip. Okay. So that is in linear regression, that's an important issue because correlation between variables will be a problem. So when you're specifying, you should specify whenever a single variable flips the sign of important variables, I would drop that variable that is causing the flip. Okay? And investigate it further. First of all, maybe something is wrong with that variable or it is highly correlated, so maybe we cannot use both anyway. So don't use them. That would be the way. So R square explains the variance is computed as the variance explained by the model, which is SSR, and divided by SST. That's the total variance in the model that you're trying to explain. So now R square is a good way to compare models, right? So if you have model 1, model 2, model 3 that you develop, whichever model has the higher R square, it explains things better. So you use it. Okay. Now let's think of a case of these models. So R square works very well when you have the same number of parameters, right? So I have three specifications here. I'm looking at number of trips, number of cars, and household size, and the variable perm here represents whether that household is a permanent household or a seasonal. So you can think of that as a big determined location. So for us, it's an important variable where you will have households from Canada who come and stay only in the winter. Okay, so their behavior will be very different than people who live there throughout the year. So we're trying to capture that with this. So here I have number of cars, household size, and permanent. Instead of number of cars, I'm using income, household size, and permanent. And instead of using household size and income, I'm using number of workers, number of non-workers, and permanent. So let's say I ran all of these three models. Whichever model has the higher R square, I can select that model as the superior model. Okay. Now, what happens when you have more number of variables? Okay, there could be cases like this. Three models. R square values are and number of parameters in the model are 5. So which model would you prefer? So model 1 has an R square of 0.5, K is number of parameters is 5. Model 2 has an R square of 0.55, it has 6 parameters. Model 3 has an R square of 0.552, the number of parameters I'm using is 100. Which is the preferred model? Okay, why second and why not third?
Even if the number of parameters that's used increases marginal or negative increase, the variance it is able to predict doesn't have its impact throughout the function.
So if I tell you all 100 of them are significant, so yes, 2 is the correct model to pick. Okay, the reason we prefer models with good R square but not a huge number of parameters is because remember, why are we developing these models? We're developing these models to predict future outcomes. Right? When we're looking at future outcomes, if I have 5 variables in my independent variables, I have to figure out those 5 variables for the future also. I'm telling you that you can. I'm making yes. Realistically, usually you won't be able to because you have 100 that are significant. R square will improve a lot more. But the main reason is the ability to forecast for the future depends on how good your independent variables also are in the future. So if I have for that 0.002 improvement, I don't want to forecast 94 extra variables for the future, right? So it is purely from that perspective. So R square is good, but it does not capture the effect of number of parameters. So that's why we use what's called an adjusted R square. Again, it's built on the R square metric. All we are doing is we are controlling for number of parameters. If your K is very large, I look for okay, is the improvement really worth the number of additional parameters? Okay, so adjusted R square takes care of this issue. So adjusted R square will help you compare any two models with different number of parameters. You can have 5 parameters in one, 12 parameters in the other. If adjusted R square is not higher for 12 parameter model, you can say the 5 parameter model is better. Okay? So it's again adjusted R square is also computed. So if you can see, it's just using SSC and SST. N is the number of observations. K is the number of parameters. Okay, K is the number of independent variables you are adding. That's how you can compare. This, if you compute adjusted R square, they would look something like this. So for these numbers, it would be like 0.49, 0.53, it would probably be like 0.43. So that would be how the adjusted R square values would look. So it's easy to compare. Then you don't have to worry about additional parameters. Automatically you can make them. Okay. Any questions? Good.
Sir, if you have no R square, then it justify them.
So yes, R square is one of the most misused metrics in transportation and electric field. Okay, so there are cases where you run a model, you get an R square of 0.1. In your research, reviewers will comment this model is very bad, it doesn't have the results. The garbage comment. Okay, because R square is specific to the data set. Okay, there are data sets where you have only 200 observations or 300 observations and the So overall processing such you'll get an R square of 0.9 without adding it. I mean, you add one or two variables, you get 0.9. Some data sets you can add 100 variables, you are not crossing point. And I had models where data sets where I think the best R square I got was 0.08. Again, R square is not comparable across data sets. It is wrong to compare it like if some reviewer comments saying that this R square value is very low, there is another paper where they got an R square of 0.6. It is a wrong comparison. R square should be used only to compare across that data set. Okay, it is used to identify the best model for that data set. So if your R square when you do one variable comes out to be 0.6, yeah, when you keep adding it will go up to 0.7, 0.8. But if you start at 0.03, it's not going to go to 0.4. So don't use it as an absolute metric. Okay, again, you don't want to be rude and reviewer comments on it, but you can talk about it saying that our explainable variance is very large and the variables we have, the overall process is such that we are not getting very large, high marks. We have tested different variables. These are not significant. So you can explain it. So R square values is useful to only to some extent. Okay, so sometimes you will have models where n and k are very big. So you have 100 data points, and let's say you estimate 25 parameters. Then R square becomes very high easily. But if you have 1,000 data points and your model only has 7 or 8 parameters, R square is not likely to be very high. It can be in some cases, but that also plays a role. So the ratio of n and k, if they are orders of magnitude different, so if it is 1,000 to 10 versus 1,000, 100 to 50, in that case R square will be much higher when you get k closer to 10. Okay, so that's also something you need to think about. So then I want to talk quickly about specification. So here I'm giving you an example model here. So you have number of trips is a function of number of cars and household size. Okay. So if in addition to this, we also want to capture the presence of permanent, whether the household is a permanent household or not. So I can add a specification. So what does, let's look at interpretation for all of them. What does beta 1 represent here? What is the, if somebody who has no idea about what is statistics comes and asks you, what does beta 1 represent? What would you explain? Physically. It should not be a mathematical explanation, it should be a physical explanation. What does beta 1 represent? So if the number of cars increase by 1, the number of trips will increase by beta. Right? Same thing for households. What does beta 3 represent? How would you interpret beta 3? So that household is either permanent, there are only two levels, it's either 1 or 0. Okay? So if it is permanent household, beta 3. Yeah. Beta 3. Okay, so households, so beta 3 represents the difference in number of trips between household that is permanent versus season. Okay, it is the difference. So if everything else is the same, beta 3 represents the difference between a permanent household and seasonal household with the same number of cars and the same number of people in the household. Okay, that's how you interpret beta. Okay, so now I changed the permanent to seasonal. Okay, I cannot add both. Okay, I cannot add both permanent and seasonal, right? Because it's only relative that you can find. So if you add it in the model, if you're running in SPSS or any software, it will drop one of them. Because once you tell the household is permanent or not, you are automatically telling the data the information about whether it's seasonal or not also. Because if a household is permanent, what will be the value for seasonal? If the value is 1 for permanent, the value for seasonal will be 0. Right? So if you have two columns which are linearly dependent, you cannot estimate two coefficients. So you can only estimate one coefficient in your model. So that's why if you have two levels, permanent and seasonal as two categories for each household, only one of those two categories can be in your model. It's like one of them is the default phase. So now I switch that around and I put seasonal. What will be the relationship between alpha 3 and beta 3? If beta 3 is the coefficient for permanent and alpha 3 is the coefficient for seasonal, will there be any relationship between beta 3 and alpha 3? So if permanent increases the number of trips they make by 0.5, what should seasonal do? Reduce the number of trips by the same number, right? So alpha 3 and beta 3 are related. They are just negative feature. Okay, if beta 3 is positive, that tells you that permanent households make more trips. So by the same logic, permanent households are making more trips. What will seasonal households? They will be making less trips. Okay, so beta naught, beta 1 and beta 2 will be the same across the two systems. Beta 3 will be minus. We will test it. In the data set, if you run the model with different levels, we will see these things. Some of that will be make us the range. So this I'm talking about categorical variables here. So we have household with number of cars and household size, and now I want to add the effect of income. And income is given as a 3 category variable: low income, medium income, and high income. Okay. Again, you have 3 levels, so we can only use 2 of those levels in your model. Okay, you cannot try all 3 of them because if you are not low income, if you are not medium income, you have to be high income. So the 3 columns are dependent. So you can only take 2 independent columns from any 3 categories. So that's why you can do different kinds of models. You can have medium income, high income, low income, medium income, low income, high income. Okay, but you cannot have all 3 in any specifications. All these 3 specifications are valid. You can choose any of them. You can run the model anyway. R square will be the same for all 3 of them. Okay, because think of it this way: the information that goes into the model is the same. If I tell them the household is middle income or not, or high income or not, I'm also telling them about low income or not. So this has 3 columns of information. Even though I'm only entering 2 columns of data, the third column is implicit, right? Because it's the same in all 3 of them, they get the same degrees of freedom, same information, so their R square will be exactly same. Now, will all coefficients be same? Not necessarily. The coefficients will change, right? Because you have here, you have medium income and high income, which means low income takes the value of 0. In this one, high income takes the value of 0. In this one, medium income takes the value of 0. Okay, so based on that, the coefficients beta 3, beta 4, alpha 3, alpha 4, beta 3, beta 4 will change. Okay, there will be a defined relationship. So if low income and medium income has a difference of 0.5, that will hold in all of these. If medium income, let's say you expect more trips from higher income, so let's say medium income is more than low income by 0.5. You will see that relationship in all 3 of them. And let's say high income is more than low income by 2, just as an example. You will see that difference of 2 perpetuated in all 3 models, but they might not give you the exact same coefficient. Okay? Everybody okay with that? Okay. So if you have k categories, so here I am giving you an example of 3 categories. So we did 2 variables. So if you have k categories, you can do k minus 1 indicator variables. It can get messy because you'll have a lot of categories. Sometimes income is provided to you in 8 or 10 categories. So then what you can do is group them into some fewer number of categories. Same thing with age. Sometimes they give you age every 5 years. Maybe it's not necessary to try all those categories. What you can do is look at 16 to 24, 24 to 45, 45 to 65, 65 and above. So things like that. That you can group these age categories and then reduce the number of categories to be testing in the model. That will help you in specification. Next one I want to talk about is what's called independent explanatory variables. So you'll notice here, instead of using number of cars, I'm using the types of cars. So in the Indian context, it would be better to say number of cars and number of two-wheelers, right? So it's very more common. So let's say here I'm talking about that. There is household size. I am splitting number of cars as number of sedans and number of SUVs. Okay. So what does beta 2 represent here? In this case, similar to number of cars, right? One additional sedan. What is the impact of one additional sedan on trip making, right? So if number of sedans increase by one, the demand or number of trips increase by two. Same thing for SUV. Okay. So now, if beta 2 is larger, what does that tell you? That tells you that sedans increase trips more than SUVs. Okay. Now, let's look at this specification. I'm looking at this specification where I have household size, number of vehicles, and number of SUVs. What does alpha 2 represent here? The coefficient. So what does alpha 2 and alpha 3 represent? Basically. That's SUV, right? It's SUV. Okay. So we cannot interpret it based on the number of vehicles anymore. So if number of sedans increase, the alpha 2 represents the change in sedans, effect of sedans. Why? Even though it is multiplied with number of vehicles, because we have an alpha 3 which is out specifically for SUVs, alpha 2 does not represent all vehicles. Alpha 2 only represents sedans. If I increase my sedans by 1, my number of vehicles will increase by 1, but nothing changes in alpha 3. So alpha 2 represents the impact of sedans. Okay? Alpha 3 does not represent the impact of SUVs. Alpha 3 represents the additional impact of SUVs on trip making. Because the effect of if SUV increases, two things change. Alpha 2 also gets it plus 1. Right? Because SUV is also a vehicle. So if you increase SUVs by 1, the change is alpha 2 plus alpha 3. If you increase sedans by 1, the change is alpha 2. Okay, so alpha 3 represents the extra impact of SUV on trip making relative to sedans. If alpha 3 is positive, it tells you people, SUVs have more impact on trip making than sedans. If alpha 3 is negative, SUVs have less impact than sedans. If alpha 3 is 0 or insignificant, it tells you SUV and sedan are the same. We don't need to differentiate. So in this specification, I can actually decide with statistical confidence whether we even need this alpha 3 or not. In the previous one, to estimate a model like this, both beta 2 and beta 3 will be significant because both are somehow capturing the effect of vehicle also. Right? Because we have 4 vehicles in the house, 2 sedans and 2 SUVs. I put 2 for this, 2 for that. So beta 2 will be, let's say, 2.1. Beta 3 is 2.3. Both are significant, but they're close. We cannot test it in that specification. But if in this specification, I'll get 2.2 for alpha 2 and 0.1 for alpha 3, and it will be insignificant. That will tell me, oh, I don't really need to worry about what type of car. Now, if alpha 3 is significant, I know that that type of car back. So this specification is an improvement. Okay, R square will not change. Okay, this and this will give you the same R square. But in this specification, I can quickly figure out whether I even need the incremental variable or not. Okay, so whenever you have interdependent variables, you should try one common variable because number of vehicles is common to all types of vehicles, and then try incremental variables that capture deviations. That will help you to figure out, okay, do I really even need the deviation or not? Make sense?
If there is a case, here we have number of cars and here we have segregated the class, right? So
Yes.
the same boils down to gender. You don't have number of people,
But you have adults and number of workers, number of non-workers, number of full-time workers, number of part-time workers. There's a lot of variables where you'll have this.
specific to gender, we have only either male or
Yeah, that will be like the first case, permanent versus seasonal. It will be like the permanent versus seasonal needs. It's a sort of, right? So all of these specifications are equal. I'm looking at specific 1 and 2. So this is the relationship between media 2 and media 3. So in this we'll pause here. Again, these specification issues are simply to give you some thoughts when you're running models for your case. So with this we covered linear regression. We'll take a break now and we'll start discrete choice models after that. Linear regression models, and we saw some aspects of how we can interpret them, how we can model them, and so on. So now I want to start looking at choice models, where we look at individual behavior in how they make their choices. Okay, so we want to look at different elements that are part of making choices. So you can think of travel in transportation, mode choice is the most common aspect where we use choice models, but it's available in different locations. So if you're looking at which kind of apartment you want to live in, or housing that you look for, or how do you want to get to work every day, or if you're looking at what kind of phone to buy, all of these are choices that you're making. Okay, so in any context like that, when you have a choice that is being made, you can use choice models for that. So today we'll learn the mathematical concepts behind how we do that. So in choice theory, basically what we're doing here is we are trying to reflect or represent choices people make in the form of a mathematical process. For that we assume that it's a sequential list making process. The first thing would be you define the problem. So for example, let's say you're trying to find phone. So what the definition would be mobile phones that you want to use. The next part would be, okay, what are my alternatives? Right? If there is no alternatives, there's no choice to me. Right? We only have one option. There's nothing but to choose that one. But when there are alternatives, you look for those alternatives. Then you start evaluating the attributes of these alternatives. For example, if you're in the case of a phone, you look at the price, right? And then maybe you look at, okay, what operating system is it? Android, is it iPhone, or is it Samsung has its own UI overlaid on Android? So things like that. Those are the different attributes. And your preferences. So right now, what are you using right now makes a difference. If you're an Android user now, probably you'll buy a new Android. If you're an iPhone user, you are stuck with iPhone in that, right? So there are attributes that you look at, and then you make the choice. Then the last step is, okay, now you choose to buy a particular phone, you go and implement. So these are what are called the actual steps that people use to make their choice. So in the context of a university travel, is an example. So this is an example I created when I was in Montreal, where you had multiple options. You can take the car, you can take the bus, you can take metro, walk, and bike. And there are different attributes for each. So there is time, the travel time, the cost of the mode, and associated comfort in that. Okay. So I'll give you the numbers for all of these alternatives. So you see here, Travel time in car is 7 minutes, 15 minutes in bus, 12 minutes in metro, 20 minutes in walk, 10 minutes in bike. The cost, car is $3, bus is $1, metro is $2, walk is free, bike is $1. Kind of fees for e-bike. Then comfort, car is very comfortable, bus is uncomfortable because you are not getting a seat probably, metro is comfortable, walk is uncomfortable. I mean, imagine minus 20 degrees weather, and bike is comfortable because you're able to wear running walk. Okay. So if these are the attributes that are available to you, okay. So which mode would you choose? How many people would choose car? You have a car, you're given a car. Okay. So you don't have to buy it. In that scenario, okay. What about bus? Okay, metro. Okay, how many people will walk and bike? Walk. Okay, bike. You have to choose something. Some people are not choosing anything. You don't want to come to the university. Okay, many of you are choosing bike. Okay, so again, when I gave you these numbers, you all processed it in some way. And again, it's not like everybody chose the same, right? Everybody is looking at the same numbers that are available to them and are processing it in a different way to arrive at the choice. So what we are trying to do in developing choice models is, can we represent this behavior mathematically? Okay? Because we cannot do this qualitatively, we need to do this quantitatively. So we are trying to assign a weight to different elements. So how important is travel? How important is travel? How important is the comfort in the service, in the bus? So if we are able to understand that, then we can figure out how people will make choices in the future. Maybe when a new mode is introduced or changes happen, travel time with different modes, travel costs change, how will future travel behavior change? Okay? So in this case, I chose walk. All I have to do is walk to work. So we'll look at the different components of this choice process. So one of the things that we need to do is we need to identify the different elements. First of all, we need to figure out who is the decision maker, right? So in the example I gave you, it's the individual. You are making a choice about whether to how to get to the university. So in that case, the decision maker is the individual. If a household is looking to buy a new car or looking to buy a new house, there the decision maker is a household. In another context, it could be an agency. So if a transit agency is thinking about changing the number of buses they own, there the decision maker is an agency and they are looking at how many kinds of buses they want to buy and so. Similarly, when the Telangana State Road Transportation decides to change the state limits or change the number of buses running between different states, their state agency is making the policy. So decision maker is one of the important elements because every decision maker has their own attributes. Right? The decisions made in Telangana are not the same in Andhra Pradesh or Tamil Nadu. So because there are different constraints, different political constraints, different regional differences, and so on and so on. Right? So the decision maker matters. Then, what are the alternatives? We need to understand what alternatives exist and how do people process, the decision maker process those alternatives. Right? In some cases, the alternatives are easy to define. There could be 3 or 4 of them. So if you think about how to get to university, there are probably 4 or 5 options. You can easily define this. But if the choice is, I want to buy a home, let's say you decided it's Warangal. But even then, the number of options could be potentially infinite, right? So you'll have to figure out a way to build the alternative first of all, even before you made your choice. So there has to be some work that goes into alternative generation in some context, not in all context, but in some context. Now, once you have the different alternatives, we need to capture the attributes of the alternatives, right? So if you, as I showed you, for different mode, there is a travel time, travel cost, and comfort level. So similarly, you might want to look at different attributes. So for example, if you're looking at a house for rent or for purchase, you might be looking at how many bedrooms are there, what is the square footage? Is it on the ground floor? Is it on the what floor is it in? Okay, different. And what is the area around the house? Is there good grocery store close by? So these are all attributes that are specific to each alternative that we can measure and then incorporate. Again, as you'll notice, the more information we can capture, the better will be the representation system, right? If you add more variables and more details about the model, then you can come up with more representative choice model than when you say, oh, all I know is the square footage of the house. I make decisions based beyond square footage, but it doesn't work that. Then the last process is what kind of decision rule is used by the decision maker to make their choices. Okay, so we'll talk about that a little bit as we go forward. So again, while I'm talking about this, it's important to recognize that we don't expect every choice to be made as a reference. Right? It's not like every day in the morning you sit and evaluate, oh, should I go by walking, should I go by bus? No, you already made the decision, you implement it. That happens. But in some cases, this is an effort by the analyst to represent people's choice process. Okay? So we are trying to mimic human behavior. So yes, sometimes we make it more elaborate than what people will do because we don't know information. So there will be some people who say, okay, I don't like to live in an apartment. I want to build my own house, individual house, right? So in those cases, they are not looking at any apartment alternatives, right? But I don't know, as an analyst, I would not have that information from the survey or because the questions might not be targeted towards. So sometimes you have components which are not representative of everybody in the population. But we try our best to get as much information as possible when we are building our. So we'll start with the decision maker. So I think we talked about it. There are individuals or groups. It could be travel mode choice, vehicle ownership, sometimes land use models. In this case, we're looking at how land use changes at a travel, traffic analysis zone or travel analysis zone level. In that case, the decision maker would be the TAC. The reason why we care about decision makers is because decision makers will have varying tastes based on their income, based on their education, based on their language, ethnicity, and so on. And they also face different choices. Right? So that's why we want to be able to know the qualities or characteristics of a decision maker. For example, if you don't own a car, car is no longer an alternative for you for that person. Okay? So when you're developing your model, you should actually eliminate car from the set of alternatives for this person. That is important to do. So that's why we need that information. In terms of alternatives, again, we can do choice models only if you have a non-empty set of alternatives. At least more than one alternative should be there. If there's only one alternative, that's a choice. So you don't have an option. So there are different kinds of alternatives available. So for example, if you look at a city like Warangal, you can say that what are the travel modes available in Warangal? So do we have? Presume metro is in proposed, but we don't have. So there's a bus system, measuring, railway, and then car, walk and bike. Right? So these would be available. But even for the bus system, it won't go to every corner of Warangal. Right? So there could be households where bus is there very far away from them. So for them, it's not an option. So the universal choice set represents all choices available in the study region. Okay. So this would be to the entire population, not to any specific individual. Then there is what is called a feasible choice set that is specific to the individual or a decision maker, right? So this decision maker lives in an area that is served by public transit. So there's a bus line that is accessible to them because there's a bus stop within maybe half a mile or a quarter mile from their house. So but they don't own a car. So if you don't own a car, the universal set car exists, but in that person's feasible choice set, car does not exist. Okay, so feasible choice set is customized to each decision. Universal choice set is all the set of alternatives available to the people in that region. Okay, now just because an alternative is part of feasible choice set does not mean the person will consider it. So for example, there are people who don't like public transit. Yes, there is a bus going very close to their house, but that doesn't mean they're ever thinking about using that bus. So that is where the third kind of choice set comes into the picture. It's called evoke choice. So this is a choice set represented by options that are considered by each decision maker. Okay? So some decision makers consider all feasible alternatives. Some decision makers don't. So if you are ideally, we would like to know the evoke choice set out of the models. Okay, but that's not always easy. Getting that information is tricky. So there are some additional questions in a survey that you can create to ask that, but that would increase the time of the survey, so people will stop responding to it. So that's why there is always a challenge to get to evoked choice. But we can always get to the feasible choice if we collect information on their vehicle ownership and where they live and whether transit is close to their house or not. So for every choice, we would like to go to the evoked choice set, but because of the cost, we always at least go to feasible choice set when we're developing our models. And then alternative attributes. So these are attributes, how each alternative is characterized. So for example, if you're thinking about vehicle purchase, right? So you could look at the attributes could include what is the square cargo space, how many seats, whether it's a now engine type is whether it's diesel, petrol, hybrid, EV, all of these are all options. So these are all attributes of the alternatives that will influence the choice process. So all of these can be considered. Again, some of them are very specific values, some of them are uncertain values. So they're challenge. So yeah. So if, for example, if you're doing a route choice, if you're going from A to B, there are 2 or 3 routes. I mean, now with Google Maps, you have some more information of travel time for all the routes. Like we were before Google Maps, so 2004 and 2005 when we were driving, we had to take these large atlas maps to drive anywhere, and we did not know what the travel time. Whatever was the experienced travel time was what we experienced. So, but when that information is available, even then you know that the time mentioned in provided in Google Maps or any of these apps might not be the actual time you experience. Because it could be an accident just before you're going, and sometimes it can be more, sometimes it can be less. So there is uncertainty associated with the value. So same thing with price. Sometimes price can be dynamic depending on how you're using it. So some of the attributes for these alternatives, they are certain, sometimes they are not certain. So we need to be careful in addressing. And the most important component of all of this is the decision rule. So okay, I have the list of attributes. So I'm saying A, B, C is important to me. These are the attributes that I consider in making my choice. Now, how do I compare or contrast with these different attributes is what we need to look at. Okay. So there are different rules used in literature. So I'll quickly list them and then we'll talk about each other. Okay. So dominance, satisfaction, lexicographic and utility approaches. So dominance rule is a very basic rule. So what it says is, if one alternative outperforms other alternatives in all metrics, okay, so in the mode choice case, that's the fastest travel time, lowest cost, and highest comfort. Okay, so that would be the term. I mean, if an alternative like that exists, do we need a model? No, right? You can obviously see that you can identify the order of importance, and then you can say, okay, for this choice, people will choose the shortest travel time, lowest cost, and highest comfort. But in the way I created my alternatives, usually you cannot find one unique answer for that, right? So dominance does not work very well because most of the times we experience trade-offs. If the travel time is low, travel cost is high. If the travel cost is low, travel cost is low, comfort is low. So one good thing means there are other trade-offs that you have to make across alternatives. So dominance works rarely. So it is possible you can use dominance to reduce the number of alternatives. If you have 8 alternatives, you can probably find 3 or 4 that dominate the other 4. So you can eliminate some alternatives, but you cannot get a unique answer using dominance. Okay. Then the satisfaction is the next rule, where you choose alternatives that satisfy your requirement. So for example, I want to go from home to work. I'm looking at different modes. I can say I'm okay as long as the travel time is 15 minutes. I'm okay as long as the travel cost is less than 100 rupees. I'm okay with minimum comfort. Okay, so what you will do is you look at all the alternatives. Whichever alternative satisfies that criterion can be potentially selected. Now, the problem with this is, again, you can have multiple choices. Right? So if there are multiple alternatives that satisfy all the 3 requirements, so it's not necessary that you end up with a unique answer. And it does not give you a way to break ties between options that satisfy. So again, this also is a good alternate, good rule to reduce the number of alternatives. If I have 20 alternatives, I can use the satisfaction rule to reduce that to 3 or 4 alternatives and then make a choice between those 4 alternatives. So for example, if you think about you're looking for an apartment to live when you're studying at the university, you can say, okay, I want maybe these 3 areas. I mean, entire Warangal is possible option for me to live, but I'll choose 2 or 3 areas because they satisfy the travel distance, cost, and other criteria. So that would be where you use satisfaction. But it does not get you to the final answer. It does not get you to one choice. Okay? The third approach is called lexicographic approach. In this approach, what you're doing is you list the attributes by the. So we have travel time, travel cost, and comfort. So one person can say comfort is the most important for me, then travel time, then travel cost. So we'll compare all alternatives by comfort. Whichever has the best, you select. If you get only one, you have the answer. But if you have multiple, then we go to the next step. So then we go to travel time. Then we compare travel times for the selected alternatives. Whichever has the lower travel time, it's selected. So only in the case of a tie, we go to the next step. So by the end of you reach by the time you reach the last attribute, you will have a unique answer or 2 alternatives which are the same for you. You can choose anything in that case. Okay, so lexicographic works in the sense that it will give you a unique answer. Right? So let's say we have comfort is the first most important one, travel time, and then cost. This is alternative 1. So because it's a type, I will look at what is the time. Okay. So this is, let's say 12 minutes. This is 13 minutes. Okay. So this person, because this person put this is the most important variable, next most important variable, next most important variable. Based on time, this person will choose alternative 1 as their option because it has lower travel. Everybody okay with that? Okay. So now I want to give you a counter example of how people make choices. Right? So let's say if this were 200 rupees, 150 rupees, let's say, this choice might be okay. Okay, you see that people, this person is choosing this because travel time is small. Now, if I make it this, okay, would this person choose? But he or she gave us this lexicographic code, right? Even if they have a hierarchy in this fashion where comfort is the most important, time is the second, and cost is the third, in a scenario like this, I'm not going to pay 1,850 extra just to save 1 minute. Right? Most people won't. So this is an example case where lexicographic approach breaks down because once you put your hierarchy, you are ignoring everything below that one. Right? Because I focus on comfort, there's a tie, so I go here. If there was no tie here, I would have made a choice here itself. Now here there is no tie, so I am choosing the alternative because I put cost as the of lowest importance. I am not at all comparing the information, but that is not true. People don't completely throw away information that is not important to them. So lexicographic approach works in some cases, but it ignores information below the tie points. Right? So in this case, we're only looking at data up to this point, but that's not how people will. If as long as it's like 165 and this is 175 or whatever, this is okay. In that case, the lexicographic approach works. But when you have significant outlier differences, lexicographic approach breaks down. So for that reason, we don't use the lexicographic approach also that much. The last one is what is called the utility approach. So this is recognizes in the 3 approaches we talked so far, we are comparing attributes, but we are not trying to interact between them in any way, right? We are comparing comfort with comfort, we are comparing time with time, or time with time satisfaction limits, but we are not looking at any interaction. So the utility approach changes that. What it does is it tries to give each alternative a scope. Okay, so what do I get by driving to campus? What do I get by walking to campus? What is the value I get? So it's a scalar quantity that is based off of all the attributes measured similar to linear regression. In a linear regression system, we wrote equations, right? We said y is equal to beta naught plus beta 1x plus beta 2x and so on. Similarly, in utility, each alternative has a score. Okay, so there is a score for car, which is beta naught plus beta 1 times travel time plus beta 2 times travel cost plus beta 3 times comfort. I can do the same for bus, walk, and so there is an equation for each alternative. Okay, so in a utility approach, we are generating a scalar for each alternative, and the person chooses the alternative that gives them the highest utility. Okay, so this does many things better. First, it actually allows us to create a mathematical equation connecting all attributes. So when you have a utility system like this, what happens is if utility score goes down because of travel, right? When travel time increases, what should happen to the utility? Will it go up or go down? It will go down. So what that means is beta 1 is expected to have a coefficient, negative coefficient. Same thing with beta 2, right? Cost of people are not going to pay more, they will pay less. So if travel time increases, my utility goes down. But because I have this linear equation, I can offset the reduction in utility in travel time by compensating in travel cost. Right? So if I increase travel time but reduce travel cost, right? So the drop in utility here can be compensated by the drop in cost because utility increases by. So this interaction was not possible in any of the decision rules we talked about. So now suddenly we can start interacting between how people value travel time versus comfort, how people value travel cost versus comfort. So it naturally brings interaction between the different attributes so we can measure trade-offs. So this is what we use when we figure out what should be the total price speed. Like how many minutes are you willing to, if you save 5 minutes, so I'm increasing your utility. So how much can I compensate for that by increasing your cost? So that way the net utility for the alternative does not change. So that is how we bring in trade-offs into the system. So utility approaches allow us to come to interact across the alternatives and then relate the coefficients to one another. That way you can start understanding what is the value of time, what is 1 minute improvement in travel time represent in terms of money, and so on and so forth. Okay. Again, I have a lot of text here and you can create this. Again, this module is already available on my website. You can just download it. Yes. So of all the approaches, the previous approaches were only useful until the 60s or 70s. Once utility approach came to existence, we dropped everything else. We are working purely on utility approaches for choices. So this is the first approach where we actually interact across attributes. So from there we go into discrete choice models. So in this, once we have utility structure, we are using an additive form of utility. Sometimes we use a multiplicative utility, but that is usually for more complex discrete continuous models. We'll talk about that later. But in this class, we'll focus on additive utility. Just take a linear regression equation. It looks like this. So we have ui is equal to beta naught plus beta 1 time beta 2 cost plus comfort. Okay. The idea is that alternative that provides the highest utility. Again, it is important to recognize utility is a scalar value. It does not have units. It has no physical meaning. I mean, utility of 75 million, 75 billion does not make any difference. Right? Okay. Yeah, but what are you measuring utility for? So here the utility comes from the choice. So in your case, what will be the choice? Yeah. So in that case, it will not. So here we for this utility to come up with this utility value, we are trying to observe choices. Yeah. So there you can use that as weights, but how you determine the weights, you have to do either expert opinion or some form of different stakeholder opinion should become. Yes, you can conclude that and then use. Yeah. Yeah. And one of the assumptions that we make, again, because of the mathematical nature of what we're trying to do, we assume that if you have three alternatives A, B, C, A is greater than B and B, utility for A is greater than utility of B, utility for B is greater than C, A has to be greater than C. Okay? So again, this seems reasonable, but there can be cases where this is violated. So sometimes if you look at different choices where there are people who will say they prefer one to the other in two things, but that doesn't necessarily translate to them preferring A to B and A to C. So it might be violated in some scenarios. So but we in our assumptions, because of the mathematical nature of what we're doing, we assume the transitive property. And another important aspect, again, I will go through this quickly, is there are probabilistic choices that we are making in this context. So, because people are not machines, right? So at least not yet. So we don't know how we can represent choice processes easily. So we cannot exactly predict everything. So we see that in our models, we estimated utility, and people are not choosing the alternative that gives them the highest utility. Okay? So then there are two ways of looking at it. One is we are wrong because our model is wrong because we're giving the wrong utility, or the people are wrong. Okay, so they don't know what to do; they're doing the wrong choice. So again, there are two schools of thought that come from this. So in psychology, they blame the people. So they'll say decision makers don't know how to make choices, so they make wrong choices. So the model is perfect; they are the ones who don't know. People in economics are a little more humble. I don't know if that's truly the case now, but anyway. So there they say the decision maker knows why they are choosing what they are choosing. It's because my model is not perfect, I am not able to figure that out. So it's error on my part. So I add an error component, or because of the unobserved component. Okay. So there is U, which is observed part of the utility. There is an unobserved part of the utility. So the total utility is always chosen based on the highest value. Okay. So if a person is choosing an alternative that I don't expect, it's because I missed something and there is an error in that equation that makes me not see why that person is choosing. Okay. So this error component is what is called missing information. Again, the psychology school of thought comes from experience with controlled experiment. So they usually what they do is they bring you to a room and they control the environment you are working in and then give you choices. So that's where they say that the choices you are making, you are bringing in error in how you make your choices. In economics, usually you don't get to control experiment. Right? So you're looking at number of employment levels, GDP, all of these. There are a lot of factors that go into play. Right? If that could be controlled, I think we would have increased our GDP much more, but we cannot do that, right? So there are different elements that go into how things change. So economics folks naturally assume that there is a randomness to how people make their choice. That part comes from unobserved elements of the choice process. So that's why our utility is no longer deterministic. We call it random utility. So there is an observed component like that, like I wrote here, beta naught, beta 1, etc. but there is something that is announced. So there is an epsilon car, epsilon bus. So each of them has their own errors, and the whole utility combination of observed and unobserved utility gives rise to the total utility, and that will be the maximum for the alternative that is chosen. Okay, and because these are all random variables, we can no longer say utility for car is greater than utility for bus. Deterministically, there is only a probability associated with when utility of car is greater than utility of bus. Okay, so from now on, when we talk about choice, we are talking about choice probabilities. We're going to say the probability of choosing car is 80%. Even if utility differences are very high, you can only provide a probability value. So we know that the chance that people choose car is much higher, but that doesn't mean no other mode is chosen.
Behavioral thinkers in psychology who are also quoted that man cannot be a rational economic man or perfectly rationalistic approach is not actually how they think. Like you mentioned about the controlled experiment. That while I'm speaking with respect to why we justify why we write a management, when there is a discrepancy in the kind of rationalistic approach we expect and there is a difference in the decisions, can we support that with the theories of Robert Simon, who tells that he's not a perfect rationalist, but satisfactory approach, or he's unlike many other economic thinkers.
Yeah, there are. So again, there are. There is a lot of research going on in understanding, making approaches.
Can you think that behavioral thinkers' observations or findings to this kind of decision?
Doing it mathematically is still not as easy. So utility approach has continued to be utilized because it gives a very nice mathematical framework. Okay.
Not about the models.
Yeah.
Why if we get the results and we try to justify the conclusions and experiments, can we make it more robust or holistic? Because
so even that is always possible. Even within the model system itself, now there are different psychological theories that have been brought into. For example, prospect theory is one. Regret minimization is another framework. Just like random utility, they look at attributes in a different manner. So just like we created a utility approach, we can create other approach. So there is this theory that people are more sensitive to loss, especially when people invest money. A lot of people. So let me give you an example. Okay? Let's think about investment option. And most of you are students, so right now you might not think of it as very useful, but very soon you'll have careers where you'll be making money. So you should start thinking about it right now. So let's say there is so this is the mean growth per year, okay, and these are the mean and max. Okay, so that means some years the minimum it could be going to these are your factors. Okay, so you can invest. Let's say you have 1 lakh rupees. You can invest in 3 options. Okay, option 1 gives you mean growth of 15%. On a yearly basis, sometimes it can go down by 20%, it can go up by 15%. Okay. Actually, let's go with 20. It's possible. So now option 2 is the mean is 5% and the maximum is 7%. It never goes negative. You never lose your money. In any year, it doesn't go down. You have the third option, which is overall return of 12% per annum. The growth pattern can go from -6 to 15%. Okay. How many of you will choose option 1? You did not ask me an important question. How long am I keeping the money for? Right? That's important. First of all, if you want to keep the money, if you want to use the money in 2 years, okay, which option will you choose? How many will choose the first? Okay, how many of you? So the time is 2 years, 20 years. So now for the 20 years month, which option will you choose? How many of you will choose the first one? It is for 20 years. Only 2. You said first one is number 3. Okay. Okay. How many of you will choose the second option? There is no right or wrong answer here, so feel free to. How many will choose third answer, third option? Where you are? There are a lot of people who are not choosing any options. So, for somebody who chose the second option, why? Why the second option, not the first one? Chose second option. Safer. Okay, so if I show you a scenario of this distribution with that mean, option 1, in 2 years I cannot say option will be better, but in 20 years option will be at least 2 to 3 times better in terms of returns. Okay, again, this is a very common, so a lot of people everywhere choose 2, or somewhat adventurous people choose 3. Okay, but both 2 and 3 significantly underperform 1. Okay, look, it can go to -20, but the mean is +15. Right, so even it goes, it will come back. Okay, especially for the age you guys are in. Again, given a long term, I'm not saying speculate in 6 months, but if you're putting investments for the long term, always choose option 1. Okay, but this is the psychology, right? Because people are not treating gains and losses the same way. If you are rational, you would put equal weight on gains and losses and you will just compute. So let's say it's 15% is the mean. So all I have to do is 1 lakh times 1.15 first year, 1.15 after, you can do compounded growth, and you can look at what will be the growth. But because you see this -20, that makes you worry. You're saying, okay, I might lose a lot of money. So again, you can, if it happens that the first 3 years are -20, yes, it will be low returns. But usually the way it works is it's not going to be 3 years of -20s. So usually it works out, especially if you can wait out for the long term. Okay, so many people choose conservative options of investment because of the extra pain they face when they lose money. So whenever there is a negative returns, that people forget the positive ones. That for the first 3 years, let's say they got 20%, but for the 4th year they lost 5%. So overall, they are still significantly positive. But because of the pain of looking at a negative number, people don't like it. So this has to be carefully considered into the mathematics of what we do. Right now, positive and negative are treated equally in a random utility approach. So there is some work going on to differentiate between positive and negative numbers and recognize how people behave. But it becomes complicated. The math behind even random utility models are hard to estimate in some cases. So estimating those models will be even more complex. Okay, but there is efforts going on, advanced efforts going on to bringing some of these theories quantitatively into the frameworks. Even if you don't take away anything from this class in the 5 days, please take away that. Okay. That will help you in your life. You need to look at, so after my PhD students graduate, I take a 2-hour session on how they should spend their money and tell them because it is work is good, but you also have to learn financial management. That's very important. And I see a lot of senior colleagues who are in their 60s who are not managing their money because nobody talked to them when they were young. You have to spend some time on it to make sure you make your choices. Because the long run, especially the way Indian stock market is, I think you can make good returns by being, again, not by wishy-washy investing, but just doing SIP. I think they call it SIP here, plan strategically. So in terms of because of the probabilistic nature of what we're talking about, so you get back to this system where an individual will choose alternative I. If there are two alternatives I and J, an individual will choose alternative I from the choice set if the probability for I utility I is greater than probability for J. Okay, so alternative I and alternative J. If you have observed utility like this, probability of choosing I is same as probability of Ui greater than or equal to Uj. This is the same as probability of Vi plus epsilon I greater than or equal to Vj plus epsilon j. This is the same as probability of going to do Vj minus Vi less than or equal to epsilon I. Okay, if I know my P's, if I know my parameter values, this is a fixed quantity. Do it from this Pi minus G epsilon J. Okay, so this I will write it as epsilon. This is some constant. What does this look like? Probability that a random variable, because epsilon I and epsilon j are random variables, their difference is also a random variable. So probability that a random variable is less than k. So if you remember your CDF functions, probability of x less than x gives you a CDF function. So this is exactly the CDF function that you have for k, evaluated at k. So this is how a binary choice model comes into existence, but for that we need to define these epsilon i's and epsilon j's, because the CDF function is dependent on what epsilon I and epsilon j are. So if I assume both of them to be normal, their difference, this also will be normal. So epsilon j minus epsilon I is also normal if these two are normal. Okay, so that will give you one more. If you assume epsilon I and epsilon j as dumbbell, epsilon j minus epsilon I will follow a logistic distribution. Okay, again, there are a lot of proofs to show this. If you have two random variables which are normal, the difference or sum is also a normal random variable. If you have two random variables that are dumbbell, their difference will give you a logistic distribution. Okay, so based on what you assume epsilon I and epsilon j, this probability will have functional form. Okay, so I'll show you some distributions. Okay. So these are, we will talk about three distributions: normal, gumbel, and logistic. Okay, these are the PDFs and CDF functions, and this is how they look when we plot. So the teal, this the bluish one is the normal distribution. The asymmetric distribution, the blue one, dark blue one, is the gumbel distribution. The orangish one is the logistic distribution. So between normal and logistic, do you notice, is there a significant difference? These are all for the same mean and same standard deviation. Okay, so if you look at normal versus logistic, yes, the normal distribution is flatter and a little bit wider tails, right? So you have more distribution around it, but for practical reasons, it's not very different. So you could use normal or logistic if there are interchangeably, if there is additional benefits in other ways. Okay, so if I assume epsilon I and epsilon j to be normal, this CDF function will be CDF of a normal distribution. Okay, that gives rise to what is called the binary probit model. Okay, when you have two alternatives, both error terms are assumed to be normally distributed, you end up with CDF of a normal, binary probit model. Now, if I assume epsilon I and epsilon j to be gumbel distributed, I get a logistic distribution that gives rise to a binary logic model, and it also gives you a nice functional form. Okay, so I'll show you that. So I'm doing the same derivation I did back there. Okay, so end up with this one, epsilon jn minus again n. I did not write the n there, n is the individual. Okay, so alternatives j and I, vi minus vj. So this would look like a random CDF expression, and if you assume epsilon an, I'll talk about some details. But so to get the binary probit, I also have to assume a distribution of the function. So it is normal 0, comma half. Okay. So when you have two normal distributions, when you're taking the difference, their variances get added for the difference variable. So when you have epsilon I going as normal 0 half, epsilon j as normal 0 half, epsilon j minus 1, epsilon j minus epsilon I will be, mean will be 0 plus 0, so mean will still be 0. The variances also add, so half and half will give you 1. Okay, so the new random variable formed as the difference of two normal random variables will be mean 0 and variance of 1. This is good because then the CDF simply becomes a standard normal CDF. Okay, so because utility is a scalar and only the differences matter, I can choose what my error term distributions should be. So I choose them to be n and 0 and half. The mean is 0 and the variance as half for both of them. So if I do that, I will get a difference term which has a mean 0 and variance 1. So my CDF will be a standard CDF, which is easier to compute. Cumulative CDF for normal for standard is easier than scaling it each time. So this is what gives rise to the binary probit. Okay. Now if I make the same assumption that they are gumbel distributed, that will give you the logistic model, because the way it works out is we will again assume that the logistic is 1, and because the CDF for logit looks like this, the theta is 1, so it will simply be 1 by 1 plus e power minus u. So u in our case is the k, vin minus vjn. So we put this minus sign here and you reorganize, it will come out to be e power vin by e power vin plus e power vj. Okay, so this is the formula for binary logic. So we have two possible systems, binary probit and binary logic. In binary logic, you have a nice formula to compute your probability. In a binary probit, you have a CDF function. And if you all remember your math, normal distribution CDF is an indefinite integral. So it requires computation We have gotten very fast. We were doing it very quickly now, but still it's not a closed form value. In the logic value, here all I have to do is I just need a calculator. I can substitute this into this equation and get my probabilities. But for probit, I need at least x so that it can compute the cumulative CD. Okay. So this is preferred because it is easier to compute this value, especially when these models came into existence. Binary probit was known much earlier. Until somebody figured out difference of two gumbels gives you logistic, they did not use the logic model because statisticians for some reason use normal distribution. So once they figured it out, then people realized, okay, we can do this much faster in computational terms. So the use of logistic regression increased a lot in the field. Okay, so we will look at going forward. I'll focus on the logic model, but again, everything we do for logic applies for probit also. We can look at it. So binary logic, the formula is very intuitive. It is exponential of alternative utility in the numerator. The denominator is exponential of all alternatives. Right? So you have one alternative here. Both alternatives come in the denominator. If I want for j, this is for I. If I want for j, it is simply be e power vj over the same denominator. The denominator does not change across alternatives. Okay, so again, there is a relationship between probit and logic. Probit has variance of 1, logic has a larger variance. So coefficients in logic are scaled higher. Okay, so if you look at it for the same data set, if you estimate coefficients for probit and logic, you can see that logic coefficients will be much higher at the ratio of 1.8. This is the ratio. You can actually check this. If you estimate both models, they will be higher by 1.8. Okay. Again, approximately, not exact, but that's a relation. So now we talk about how we can use these models here. So if you have drive and transit as the alternatives, you can have equations like this to determine this utility for both of them. So you get VD is a constant for drive, constant for transit. But because only utility difference matters and there is no absolute value meaning for utility, we cannot estimate both of them. Okay, all we can estimate is if you look at this equation, it's only a function of Vin minus Vjn. Okay, so I can get, for example, Vin minus Vjn is 2. I can get 2 in a million ways. Right? I can get 3 minus 1, 2 minus 0, 0 minus of minus 2. But so we cannot figure out a unique value for utility. All I can figure out is a unique value for the difference. Okay, so that's why to make our life easy, we can take one of these 0. We can say Vin is 0 and find Vj, or set one of the constants to 0. So that's where the idea of the base comes in, because all I can estimate is the probability is a function of difference. It does not care what the absolute values of Vin and Vjn are. All I care about is what is the difference between the two utilities. If the difference is 2, that's what gives me a mechanism to find my VTs. Okay, so that's why whenever we set, for example, VD to 0 for drive, we set it to 0 and find utility for transit. So we don't need to do both, we can do one of them. Okay. So here is an example of both models. So I am giving the different variables. So AST refers to alternative specific constant. In vehicle travel time is IVTT. Out of vehicle travel time is OBTT. Cost and income. Okay. So all of this information is given, and I'm just substituting with coefficients here. So you'll see the coefficients, the way I created this problem, the coefficients for logic are of a higher magnitude. So if you take the ratio, they will be around 1.8 times higher. So you can use both of these approaches and find the probabilities, because you know the coefficients. All you have to do is multiply each element with the corresponding coefficient. Okay. So minus 1.3 times 0, minus 1.04 times 12, 0.06 times 7, and so on. So I'm computing the utilities for you. So the utilities for drive, for probit are 1.5, for utilities for transit are 2.59, logit 2.7 and minus 4.67, and then I'm computing the probabilities. The top row probabilities are computed using the CDF function. The bottom row are computed using the utility. So e power minus 2.7 divided by e power minus 2.7 plus e power minus 4.6. That's the denominator. That gives you 0.88. So you'll see that both models don't give you exactly the same values for probability, but they're pretty close. So if you're using the probit model, you will say 86% chance they'll be right. If you're using the logic model, it's 88%. Okay, does it make sense? Any questions? Okay, so if somebody gives me these coefficients, I know how to compute the probabilities. But how do I get these coefficients? Right? In linear regression, we used the idea that we want to minimize error to come up with the coefficient. So we said we want to minimize y minus y hat square and 1 and alternative 2. We know which is chosen. Okay? So now utility is an unobserved construct we create to help us figure out what is the choice. So now we want to figure out the unobserved things, right? But we have something observed. What do we have observed? The chosen alternative is observed. So if you have a perfect model, okay, what should be the predicted probability for car for the first person? Okay, 1. So we'll use that to derive our betas. Okay, so what we'll do is, if I have a perfect model, it will predict 1 for car, 0 for bus. 0 for car here, 1 for bus. 0, 1. Now, so what we are trying to do is we are trying to predict the sequence of choice. So I should be predicting car, bus, bus, car, bus. This is what I need to be predicting with my model. If I don't predict this, so if I predict 100%, I have 0 error. If I only predict 60%, I'm making an error of 40%. So I want to minimize that error. Okay, so one approach could be probability for the chosen alternative. Okay, so let's say, as an example, for the chosen alternative, I'm predicting this. So I can compute error 1 minus 0.6 square and use that as a metric, right? So I can compute this for all of them and I can minimize this, just like what we did in linear regression. Okay, but there's a small issue with it because in linear regression, the y minus y hat goes through a large range because my y's can be 5, 50, 100, 250. My predictions can also be huge. Here, we are between 0 and 1. The largest error is 1. The smallest error is 0. Right? If you predict 0 for the probability, if you predict 0 for the chosen alternative, your highest error will be 1. If you predict anything else, it will be less than 1. Right? The smallest error will be 0. So the range to make improvement is very small. So we don't use the square approach here. We actually take what is called the log likelihood. Okay, so what we do is I directly take ln of the predicted probability. So what will happen if I predict perfectly? Ln 1 is 0. So I get no error if I predict perfectly. Anything less than 1 gives me a negative error. So I add all of this up and then I try to maximize it. Because it's a negative number, when I'm trying to maximize it, I'm trying to bring it as close to 0 as possible. So this maximization approach gives you a mechanism to solve for your beta. So you write the likelihood function as ln of the chosen alternative and then maximize it, differentiate with respect to beta. You get a mechanism to find betas. You won't get a formula to find betas. But does this approach come through? Is this coming through? So instead of trying to take the difference of the probability here, we're actually simply taking the ln of the predicted probability. If I predict 1 for the chosen alternative, if car is my chosen alternative, and if I predict 1 for the chosen alternative, I am contributing 0 error to my function. Anything less, I contribute a negative error. So I maximize that function. I get the best possible values for the meters that give me the lowest possible error for my mode. Okay, that's what we do. Do 1 minus probability, but so the likelihood function is predicted probability for the chosen model. Okay. So we like to do this as a matrix. So here I have to keep track of which probability to consider, right? I'm considering car probability here, but am I considering the bus probability here? Do I care about the bus prediction for bus probability? Why? Why am I not considering? Shouldn't I worry about? I'm only maximizing the car probability. Is that enough? Because car and bus add up to 1. If I maximize car, I am automatically minimizing the bus. So I don't need to worry. So in discrete choice models, we focus only on the chosen alternatives. Because if I improve the chosen alternative, I am automatically reducing the share of non-chosen alternatives. So if I make a good job with car, I'm automatically doing a good job with transit. Okay, so that's why we don't worry about the non-chosen alternative. The log likelihood is only focused on the chosen alternatives. So if you look at the chosen alternatives here, I have to keep track of which is the chosen alternative. First one it's car, second one it's bus, car, and bus. So I need to focus on the car probability here, bus probability here, car again, and bus again. Okay, so I do this in a matrix form in this fashion. So you'll see here, we write the likelihood in this fashion. So for each person, we do both. We put PDN and PTN. PDN is drive, TN is transit, but I add delta DN and delta DN. So this delta DN and delta DN are these columns, the 0 column, 1 column. So if the person chose drive, delta DN will be 1 and delta DN will be 0. So that second term will collapse. Okay, so that way I don't even have to worry about which is which. I just use that matrix columns appropriately. So this is how you do your log likelihood. So for each person, it's automatically selecting drive if you chose drive, it's selecting transit if you choose transit. So this is your log likelihood function. We take the log of this, because again, product can become computationally intense. So we take the log, then it becomes a nice summation function that looks like this. So the log likelihood function is delta dn times ln PDN plus delta dn times ln PDN. If delta dn is 0, this will drop off. If delta dn is 0, this will drop. So for any person, only one of these two terms is active, right? Because any person can only choose one alternative. Either they choose drive or transit. So if they choose drive, this will stay. If they choose transit, this will stay. The other will become 0. Okay. This is the function that will maximize. So if you looking at the maximization, you end up you have to take the derivative of this function with respect to beta. Okay. Now it's a little challenging because remember, PDN is probability. We are not seeing beta yet. Beta comes in because there is the utility formula, right? There is a formula for probability. E power beta by E power beta plus E power beta is there. So these derivatives are not going to be very simple. They are still, because it's exponential function, not that bad, but we will have to do this. So you have to do the derivative for each of the betas, right? If there are 10 independent variables, you have to do it separately for all 10 of them. But the same mathematical structure translates, so it's not, you don't have to do it repeatedly. And when you take the derivative and set it to 0, you will have this equation. You can do anything you want with this equation, you won't get a formula for it. Okay, so we need to use numerical solutions to find the value. Okay, so you have to use gradient search methods. So you start with all meters are 0, find the objective function value, then you plot the gradient at that point for this function. I think I should have a slide where I show this. Okay, I'm deriving it. I don't want to go into that detail now. So we use something like this. So you have a function that goes like this. So what you do is at each step you are computing the gradient. So let's say we start at this point. Okay, then you find the gradient and the direction tells you whether you are optimal or not. When you are here, you are not optimal. You know you have to come to the left to bring it to the optimality. So you can, two things we need to decide. One is how far do you jump from here and which direction you need to jump. Okay, so these are decisions that are being made. So when we start here, the gradient angle tells you which direction is the optimal function, right? Because you want to go to 0. Your objective, your angle is like this. You want to come to this side, so you come this way. So when you come here, you realize you're closer. You find another point. Then, so you keep moving along this curve to find, here it's a minimum. We're trying to find the minimum. So this is the Newton-Raphson method. Okay, so we use different approaches like this to iteratively get to the point where there is the minimum here, or in our case, a maximum. The curve is upwards, but it's the same approach. So we're trying to find the maximum through an iterative process. If you are running any of these models, you would have seen iteration 1, iteration 2, iteration 3, and so on, because the solution is obtained iteratively. You cannot have a single shot answer. You will get that iteratively. This is the main equation that you will get, that you need to set to 0. This is the gradient first order condition for the objective function, maximizing the objective function. So all I'm doing here is taking the derivative of this. So getting this part is easy. You have it like this. I have the ln PDN. PDN is a function of beta. So derivative of ln is 1 over x. Ln, if you take the derivative of ln x, it's 1 over x. So that's why you get 1 over PDN here. And then, but you have to take the derivative of what is inside also, PDN over beta. Similarly for that one, it is delta Tn 1 over PTN over derivative. Okay. So I want to see the expression for binary. So again, I've worked out the derivations here. In the interest of time, I'm not going to go over each of these, but there is a little bit of an elegance in terms of the binary logit expressions. So it works out. It simplifies reasonably well. Yes, they look long and they look scary, but it simplifies reasonably well. So you get nice formulas that you get. So for example, this is the formula you get for the first order condition. So you'll see delta dn minus pdn times xdn plus delta tn minus pdn times xdn should be equal to 0. So if your x happens to be only an alternative specific constant, which means only 1. Okay, so if you have that, and you only need to have it for xdn, xdn will be 0. So if you use this, you will end up with, the gradient will end up at 2. So you're basically saying this drops off, xdn is 0, so this part of the curve is gone. So sum of tn minus ptn times 1, right, is equal to 0, which means share of the probability that you get for transit is the same as the observed share of transit. Does everybody see that? See, if you add this term, right, delta tn minus ptn, what is the sum of delta t? Delta tn is 1 if you chose transit, delta tn is 0 if you chose drive. So if I add all delta tn's in my data set, if 30%, if 300 people choose transit and 700 people chose car, delta tn will be 300. If I add that summation of delta t. So my sum of all of that should be equal to the predicted probability for a transit. So if 300 people chose transit in a data set of 1000, my total predicted probability for transit will be exactly 300 or 0.3 for each person. If you're using only constant. So your constant will give you, just like in linear regression, constant model here gives you good information. It tells you what are the sample shares in your data set. If your data set is 50-50, your constant will be 0. Okay? If your data set is 30-70, your constant will adjust in a way that the predicted probability for the chosen alternative is aligned with the share of the sample. Okay, so you'll get sample shares. Hence, when you only use alternative specific constant, sample share is same as the predicted share. So again, this will become our benchmark. Okay, just like a model in linear regression, the constants only model gives you exactly the same estimates as what you will get from an observation of the distribution of sample shares in for bus and transit. Okay? So this is the equivalent of the sample mean information in linear regression. So if 20 people choose transit, you can estimate transit probability as point. Okay. So now another thing that you can do when you have a two alternative case is, if you have two alternatives, what is your blind guess for the choice? 50-50, right? If you have two alternatives, so that is the ultimate benchmark in any model for this picture. But it is the wrong benchmark, right? You can use 50-50 as a benchmark if you don't even need it. But when you're estimating a model, you know what is the share in your sample. You know what is the share of public transit, what is the share of bus, car. So why will you use 50-50? If you use 50-50, it will make any model you develop look better. So that's why some people use the equal alternatives model as a benchmark, but that's not a fair comparison. Yes, we'll talk about metrics like rho square, which are like R square. They will look better if you compare with the 50-50 model. But in reality, when you have information on the actual observed shares, that should be your benchmark for you. Okay. The approach is called maximum likelihood approach. This is generic to any approach. So the log likelihood process that we created here, if you're using multinomial logit model or multiple discrete continuous models or any advanced models, the formula starts right here. We use the same idea of estimation. So we don't revisit this. Only thing we're doing is changing the formula for probability. So maximum likelihood approaches are very generic and they work very well for a whole suite of models, and we use those going forward for every model that we discuss in this class. So we'll talk about goodness of fit measures. It's getting a lot of math equations. So these are the benchmarks that we use. If you have equal share model, so what this means is, if you have two alternatives, the blind guess we can make is half and half, right? So that is what gives you a log likelihood for L of 0. So all I am doing here is, if I have n records and if I have k alternatives, n ln 1 over k. So because if it's two alternatives, it's half, ln half. So this will give you the log likelihood at 0. Okay. Then the second part is called constants only model. The constants only model represents the sample share. So here, if you look at it, 2 here. So this is 2 and this is 3. Okay. So when you are computing the equal share in this case, but there are two alternatives. So the equal share log likelihood, or L of 0, would simply be 5 ln half. Okay, there are 5 records. Each of them is 50-50. So that will give you 5 ln. This is one value. Then if you want to do the sample share log likelihood, I call it L of C. L of C is computed as 2 car. So 2 ln 2 over 5 plus 3 ln 3 over 5. Okay, so I'm computing log likelihood for all 5 records. So in the first model, the blind model, I'm just doing half, 50-50 to each of them. So I'm doing 5 ln half. Okay, so in this model, so this is the dumb model where it's saying, oh, both alternatives have 50-50 chance. So I get a log likelihood based on it. Here what I'm saying is, because I observed that car is 40% and transit is 60%, I predict 40% for everybody with car, 60% for everybody in transit. So 3 times I get lucky because I'm predicting 60%. So for 3 people, I'm predicting 0.6. For 2 people, I'm only predicting 0.4 because I'm predicting the same value for all. So I get a different log. So can somebody compute these values for me? What is 5 ln half? Ln 0.4 plus 3 ln 0.6. Three point 3.6, 3.3, so it should be smaller. Sorry. Okay. So this is the worst log likelihood you can get for your data set. Okay, so 3.46 should be the extreme limit of the error. This should always be better than this. The worst is at most it can be equal, but this should always be higher. So any model we develop now should be better than this. Okay, so if it is not better than this, then it no need to even look at that model. That something is wrong with it. Okay, so these are the benchmarks. So that's what I'm doing here. L of 0, L of C. If you have a perfect model, it will be 0. So what happens is, so L of 0 is somewhere here, L of C is somewhere here, and our model. So this is the equal share model, this is the market share model, and hopefully the model that we estimate will be somewhere here between L of C and C. That is how the structure will work. Okay, so now once we know this, these are the different measures that we can use. Rho naught square is computed as L of beta is what you get from your model with independent variables. L of 0 is what we are computing. Similarly, there is rho c square. So this is comparing with equal shares. This is comparing with market shares. Okay. Again, rho naught square will always be higher than rho c square, but rho c square is the more accurate one to write. Just like we have R square and adjusted R square, there is a penalty for parameters used in the adjusted rho system. Okay, so these are all metrics that come. If you know L0 and LC and your log likelihood for your model, you can compute any of these metrics. Okay, any questions? Okay, one more slide. Let's stop up. So there is some measures that we can use. Rho square, etc. can be used, but we can also use some other measures such as average probability of prediction. So you can look at predictions from your model. So let's say you develop a model and you get predictions like for car 0.7, for transit 0.6, 0.5, 0.8, 0.7. If you get something like this, you can actually check whether they are more than 0.5 or not, and say, did you predict correctly or not? Okay, that's one way of doing it. I'm not a big fan of that because you can get it to be correct by doing 0.51 and 0.49 all the time, right? Because that doesn't necessarily mean much. So, but a better metric would be what is the average probability of correct prediction. So, what we do is it's not just enough to get 51% and be right. Are we getting 70% and then we're getting it, right? So, if I measure this and take the average, I'm getting 0.75. Which is good. At least 75% probability I am getting the bus option. So I can look at the same for car option. So 0.6, 0.5 and 0.7. So it's about 0.6. So I'm getting 60% of the bus options correct that. So we can discuss that could be a way to do prediction. But overall, log likelihood is the most preferred metric. Okay, because log likelihood penalizes poor predictions severely. So if you look at the numbers at the bottom, so if you predict 0.9, this is the log likelihood contribution. Obviously, if you predict 1, it's 0. But as you do worse, it multiplies not just square, it multiplies exponentially larger than that because that's a log distribution. So if you have a very poor prediction, it puts a lot of weight on your log likelihood function. So it does not allow to have such bad predictions in your data. So this is more useful than any of the other metrics. So that's why we tend to keep using log likelihood as a benchmark measure for looking at how good the model fits. Okay. So I'll pause here and we'll look at some models in the afternoon as a tutorial. I think are we doing it here or in the lab? We'll meet in the lab afterwards. Okay. Thanks. So data associated sample data and codes you can download. So you download both of them. Click on this. It should be a zip file that you can download. And then answer that also do the same with this one. And you can actually practice running linear regression and binary logic. Okay? So if you start, if you have any questions, then walk around and take it. Where syntax for the model is here. You can change this is the dependent variable, log y is a relation variable. You can try different variables and see how you can improve the master value. So select all the run, we get results like this. So ensure the code runs first. If it works, then you can start making changes. First, you have the also the data set label here. Riderships and Apple.com. We are trying to specify. I already placed all the variables in your data set here. You can just copy from here and put it when you are trying to specify the model. To source file location. Okay, if it's not running, the code, if the code runs, once you extract, it's okay. If the code doesn't run, do this. Then it should go. Okay. So again, I just put some independent variables here. This is not the best model. I just gave you a code that works. Now you can start looking at, okay, what should I use among these variables here to improve the ask. Okay, so you can work on it. So if you change any of them, you can if you want to add, just put plus and the variable. These are all the beta x1, x2, x3, x. Okay, you can keep adding here and just run the model. It will run and it will give you new results. So you can look at R-square values here. You can see the R-square value. Now add variables to make them higher and also make sure the coefficients are significant. If something is not significant, drop them. For example, in the specification I gave you, SFQ 6 plus is insignificant. And that is low. Okay, so you can drop that variable and add newer variables from this list. sure you look at the R square value. You're improving the R square. Right? You want to keep adding variables, so you increase the R square from whatever it started. Definitions are available in another file. If you're looking for what these variables mean, because these labels don't have enough information, you can look at the variable definitions in that file. The readme for column header. This has the name explanation for each variable. So if you want to know what is SFQ 0 to 3, here. FRQ, ACOM, all of these have names, definitions. So this code you can use for any linear regression if you want to. So all you need to do is change the file name. Obviously, you have to use your file. So if you want to practice with it, you can use it for any case that you have. If you collect data for your research or any at work or so on, you can use it. So just if you can practice, placing destinations around. You don't need the volume. And then those conditions very good by station. Yeah, they might be no questions. But even that, so yes, friends, it's not just about how much revenue is generated. Why brain? So based on usage, if people are picking, you can figure out. So maybe that really happens. That a lot of people are picking up the protein, starting at the next station. Yes, you will have data. Thinking that so yeah, she was actually doing some of the So if I'm thinking from one metro stop to metro to commuter rail is easier than metro to bus. Because bus you have to walk on the road. So add evidences based on the distance. That's the extra penalty. So we create those connectors like that. And then what I will do is look at travel times or populations. If you have the population information, you can see how accessible the system is to the margin. Forget the destination. So if I'm living in a particular area, how far is the nearest connection to the grid? Okay, and can you come up with distance matrices or time matrices and figure out get from that also accessibility basically to any of the systems. It would be a you have nodes in each bus stop, each train. There are three nodes. So that 5 minutes gives you 10 minutes. So you can see the deserts. So you also need the book. You need to bring in the impedance, frequency. Yes, metro stop and bus stop close by. But if the bus stop comes only once every 3 or once every 8 months, so you need to impedance. Yeah. Impedance. Yeah. You can create 3 or 4 categories of that, and based on that, or you can make it a function of frequency. So frequency is once every 30 minutes. It's a 30-minute impedance, right? Because it should be less than 30 because they're single metro. I don't know if you have the service detailed service information. Yeah, exactly. Then you can, if you have frequency, room. Will get higher than 0.55.
Should I consider all chipping? I considered all the
Consider all the variables, but the sensitive aspect, right? So it will.
yeah. So adjusted is around 0.5.
5.3. Okay. All of you got close to 0.5. Okay, and all the variables are significant in models. So what is said? What is the criterion? How much? 90% or 95%? What did you use as cutoff? What are the t-stat value? Lowest t-stat value that you have? For this one, I got 0.55. Again, you can look at it. It's okay. Okay, the objective is not to get the A, but I just wanted you guys to practice. I added the variables to object of them. I dropped some of them and added. Okay, so now is everybody comfortable with running linear regression? In the future, if you get a new data set, you will be able to use it. So you can identify your y variable. All you need to do is change the y variable in this specification, and then you can see the output that you get from the. So now let's move to the second part. Let's look at binary glass. So this one, I think this is the model again. So again, make sure to do the same thing. Download it, unzip it, and then set working directory. Then it should run. So this is a binary model. Let me explain the code. So the data set, there is a PDF file which tell you what is the data set for. And here we are using two alternatives. So I'm using air and rail as the two modes for this data set. Okay. So utility is computed for air and rail. Then you are running the model for the specification. You will see alternative specific constant, coefficient for rail, air, access, cost, and no frills. These are the and there is Wi-Fi present and food is present or not. Okay, these are all the variables that I am giving. Again, you just select the code and run, but it is for these two alternates. Now here you can again change the coefficient if you need to, but I want you to just run and look at the data. So we're using air and rain as alternates. So in regression, there will be fewer things to change. When you are running a code, all you have to do is give the y and independent variables. Here you have to do a little bit more work, right? So you have to figure out, tell the software which is the dependent variable. Here we are telling that the dependent variable is a equal to b, rain equal to 4, and I'm providing information on availability and the choice. Choice is the column that has information on the choice. So if you look at the data set, we're only using SP for this one. So it is what it does is it takes this Excel file, it takes the data and samples it. So to do what we are doing, I'll show you there. First step there. Here, you look at database. Started, took the entire database, and then it selected subset of only when SP is equal to 1. SP is a column in your data set. So all SP equal to zeros are thrown in. Then it's saying choose only when choice is 3 or because if you are looking at binary, it's creating a binary data set. So only choosing when the alternative is either 3 or just that way we are reducing the set. So if you look at the data set here, it has RP and SP. Okay, so the first step in that code, and it selects out only SP, these 0 rows are removed. Okay, then it goes to the choice. So this one, choice can be 1, 2, 3, 4. It's selecting only 3 and 4. Okay, so that's what it's doing with this step. So we get a data set. That is the data set on which we are running our code. So we only are taking air and rain, and then we are running our model. So we create, we won't have to change. So this here, what we are doing is we are giving the starting values for our parameter. So in a linear code, optimization is easier, so they don't ask you to give any starting values and so. But here, again, whenever you add a variable in your utility equation, it has to appear here also. So the utility equation comes here. So this is ASC rain, it has to be there. ASC air, it has to be there. Okay, so all of these beta parameters have to be included here, and they should have a starting value. And because we have two constants, see I put two constants. Okay, one way of writing the utility is you don't put constant here, but it's 0 anyway. We know we don't. So you can do it that way, or you can put it and say it's 0. Okay, here it's a command called fixed. So if you put any variable here, it will be fixed to whatever you start. So if you put 20 here, it will fix to 20. You can fix it to anything, not only 0. But again, in our case, we only have to fix it to 0 because we are saying that has no impact. We only can have one constant. So we fix 2 of these to 0. Okay? Because b underscore no frills is variable you are adding in this one. So if you look at the dataset PDF, you will see what is that. So if you are going on a air service, there are like Indigo versus Air India, and there is no food on Indigo. When you fly on Indigo, it's a low cost service, so there is no food. So there are no frills. That's what frills means. So if you go on a full service, they will bring you drink for even a 2-hour flight. They will bring you a drink, they will bring you food and all. But then they charge you extra. So they're trying to figure out the impact of that on the utility of choice, right? Then obviously there is time for air, time for rail, cost for air, and cost for rail. So all of these are considered in this variable. And same thing for Wi-Fi. Are people willing to pay extra for Wi-Fi? What is the impact of that on the service? So So we reach this and this to 0, so they remain 0. Everything else is estimated. The utility is estimated. So now you have to compute because you have the rail terms and the terms that are common. You can actually write the utility using these equations. Right? You have the coefficients beta times x1 plus beta times x2 plus beta times x3. So you can compute. Okay. So what you can do is you can see. You can change any of these variables and add new variables to the data set, see if there is anything that you want to add or drop, and see if you can change. So practice how to run. So whenever you change a coefficient here, this is not as simple as the linear regression one. You have to update here also. Okay, if you drop the coefficient, for example, if you change the utility here, you also make sure that it is updated in this way. Okay, because you should have the same number of parameters both in the starting vector and in the utility equation. You cannot have something only in this and not there. Then it will say well. Okay, so if you make changes, so let's say you want to drop the food variable. Okay, so you drop everywhere. You have to drop it here also, there also. Makes sense. So run the code and see if you can get to. And then they gave all the different row square, all these numbers that we discussed in class. Some of you might have to install the Apollo software, Apollo package. You have to install. Yeah, so this line is commented. You can uncomment it for the first time. Okay, so uncomment that because you might not have Apollo on your studio, so you have to uncomment it first time. Once you do that, you can put a comment afterwards. Don't need to install it. Email does not change the proxy order. Yeah. Beta times x. We remove beta. You have to remove x also. Otherwise, it's trying to find the beta. model with three alternatives, and we can compare the two models and see how the code works and also how to specify it better. So we'll do that tomorrow. And those codes are also available already. If you are interested, you can always go there and download it. It's there. But I'll go over them.